help if I turn the microphone on. Testing 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. I'm waiting for it to come back through YouTube into my headphones. Should be here any second now. Testing 1, 2. Testing 1, 2, 3, 4. Testing 1, 2, 3, 4, 5. Trying to bring the level up. Okay, that helped. This should help even more. 1, 2, 3, 4, 5. Testing 1, 2, 3, 4, 5. Testing audio mics, audience mics. Testing other audience mic.
Jonathan Rizzo, paging Jonathan Rizzo. No, you're a Jason. Okay. No, go ahead. You just walked up here like you were a Jonathan Rizzo. Okay, we'll get started here in just about 3 minutes. You ready? All set? Okay. And we're streaming. Gary, you ready? Okay. You ready? Okay, let's go ahead and get the Saturday portion of the Digital Communications Conference going. Welcome, everyone. Good morning. Oh, good. Everybody's awake. This is wonderful. How was everything yesterday? Well, good. If you have any comments or suggestions, let me know. We're always looking for ways to expand and improve upon the Digital Communications Conference. So let me welcome you again to day 2 of the Digital Communications Conference, the 41st annual, in partnership with the ARRL. My name is Stephen Bible, N7HPR. And we have a pretty full schedule today. As I mentioned, I want to say welcome, and also a reminder, smile, you're on YouTube, and what we want to do is, and this is something we weren't very disciplined in doing yesterday, we want to make sure that you get a microphone when you have a question. Otherwise, the people on YouTube really don't hear anything, okay? You won't be picked up on the mic. So wait until we can get a microphone to you and ask a question. That benefits all those that are watching. Yeah, and a good practice anywhere you're at is, as a presenter, to repeat the question. It's always a good practice for that. Yeah, rephrase. You can rephrase it. You can make sure you understand the question. That's true. Okay, we'll be following the schedule today. So we have the main session here, and if you're interested in the introductory talks, we have a second track. If you go all the way down the hallway and take a right, the room is Yorkmont A, Yorkmont Alpha, and at 9:45, just as soon as we finish up with the welcome here, is Introduction to System Fusion Digital Voice, and this is being presented by Mark Thompson, WB9QZB. Now, for those that are on YouTube wondering about the introductory sessions, we're not streaming the introductory sessions, but we are recording them, so they will be posted up on the TAPR digital channel. So you catch those hopefully here pretty quick. Okay, so George says give them several weeks to be able to format those videos and get them posted. At 11 a.m. is Introduction to High Definition Digital ATV, and the A stands for amateur, TV stands for television, kind of an antiquated term, but it's still a fascinating technology, especially with the digital aspects of it. And this is Mel Witten, K0PFX. And then that leads us right into lunch today. Want to remind everyone that we have lightning talks scheduled right after lunch. I already have in my hands here 4 talks. Actually, yeah, I have 4 talks scheduled right now. So we'll have room for more talks. If you're interested in doing a lightning talk, get a piece of paper. There's some tablets that are out in the hallway along with pens. Write down your name, the title, your call sign, and hand it to me, and then I'll call you up. If you've got slides, put them on a thumb drive, and we'll pop them into the computer so you can present them. As you saw yesterday, some folks used websites. So if you have a website that you'd like to do, we'll bring up a browser and queue that up for you. So we have the lightning talks today right after lunch. And this, of course, is a screen capture of the proceedings. Yesterday there was a problem with the bit.ly short URL for the schedule, so I'm just going to simply say go to tapr.org. You can get the schedule there. You can also get a link to download the PDF of the proceedings free. And if you would like a printed copy, there's a print on demand. It's lulu.com. It'll cost you $10 plus shipping to get it printed. Now, today's sessions, many of the talks today are in the proceedings. Okay? We also encourage you to fill out the survey, and you'll see the URL on the bottom there. It's very simple, tapr.org, TAPR DCC review. So we highly encourage you to get us feedback on how we're doing. Lunch is going to be the Fiesta Buffet. We'll be breaking for lunch at noon, and then we'll be back here at 1. So here we've got your choice of beef or chicken, vegetables, tortillas, various sauces, rice and beans. Go easy on the beans, guys. Okay. Okay. And your afternoon break today, no sugar today. Today, well, yeah, there is sugar with the Cracker Jacks, but it's more of a salty one. So we've got popcorn, Cracker Jacks. We got soft pretzels, salted with mustard, mini corn dogs, and then there's going to be root beer soda, coffee, and tea. So look forward to that. That'll be at 2:30. Then we're going to finish the talks. What I should say before I put that up there, I should have put a slide on it. I apologize. We got afternoon talks. We got several that are recorded that we're going to play, and these are presenters that have submitted papers, and they were unable to make it here. So we have 3 recordings that we'll be playing this afternoon after the break. We'll go into the TAPR annual meeting. We encourage all of you to attend that. It's optional, not mandatory, but we usually have a very big crowd. The annual meeting's the opportunity for the TAPR Board of Directors to give you their reports on their various duties. We'll also give you a treasurer's report. We'll show you exactly the monies that have been taken in, especially ARDC grants, what we've been doing with them. So we're making a full accounting of what we're doing at that meeting. So we'll do that in the afternoon. Chances are we'll finish a little bit early and we'll just go right into the annual meeting. We'll take about an hour for that. Then after the meeting, it's playtime in the demonstration room. And then 6 o'clock, the bar is open. And now this time we don't have the free beer and wine set up for today. So alcohol you pay for, beer, liquor, wine. However, TAPR pays for the sodas on that. And the location of where the bartender will be is over in the same location that we had lunch and the social yesterday. That same location is the banquet tonight, and here's our menu. It's the savory dinner buffet. So we're gonna have salads, mushrooms, cheese, wild rice, and then we have your choice of chicken or beef, and various starches and vegetables and desserts as well, coffee and tea. So that'll be tonight. Tonight, our guest speaker is Rosie, the executive director of ARDC, talking about her experiences. So we're looking forward to that. After her talk, we'll have a brief award ceremony, and then stick around for the door prizes. We have lots of door prizes. We have so many that just about everybody here will take something home. Now, for lunch, you've got the green ticket, so present that for lunch, but for the drawing, you want to put your name and call sign on the small piece of the ticket, put that into the bucket, and we'll do the drawing and call your name and call for the different prizes for that. And then I want to briefly say tomorrow for the Sunday seminar, John Hayes is going to direct these talks. And I totally spaced out that I put on the calendar we're starting at 8 a.m. So it was like, okay, we start at 9:30 Friday and Saturday, and then I punish you on Sunday by coming at 8. Now breakfast will be set up at 7. So if you're interested in grabbing a breakfast, come on down early, but we'll get started at 8 tomorrow. And here's the list of talks that we're going to have. For Sunday?
The weekend at 7, weekdays 6.
Okay, so the hotel restaurant starts serving breakfast at 7, if you're interested in that. And that does it for the welcomes now. Any questions or anything I missed? Okay, then enjoy the rest of the day. And thank you very much. Jason, come on up.
Okay.
Check, check.
Check, check.
Okay. And Gary? Okay. Jason? Okay. And Bruce? Sorry, George. Yeah. I'm running on fumes this morning. All right. Jason Roush is going to talk to us about packet or APRS. Man, the fonts just really got boogered up, didn't they?
Apparently
Okay.
when it squeezed it down.
Yeah, ESP32 packet and APRS. Take it away.
Okay. Okay. So I find that these three tend to cover. So good morning, guten Morgen, and dobry utro. It's just a little joke of mine. I can see no one's laughing, so apparently it's my joke. All right. And Jason, I'm sorry. I'll try not to walk around. It's my habit, so I don't get too stagnant here. So, okay, so let me give you a quick little background on me and Remy Bilodeau, who's actually watching live right now from Quebec. So I have to make sure I watch what I say about him. I live in Chesapeake, Virginia, and I've been licensed 28 years. My main focus in the hobby has been APRS. DMR, P25, and I do get into a little bit of QRP HF, which is when I go camping, basically. By day, I'm a Motorola systems manager, so I actually work for Motorola, and I used to be a field tech. And at the beginning of the year, I switched over, and now I'm a desk jockey. I became the enemy. I'm a manager now, so. At night, I say I'm the owner, engineer, and janitor at RPC Electronics. So that's my quick little plug for myself. Remy, he lives up in Quebec. I think it's Presaic. I think I'm pronouncing that correctly. Remy, I'm sorry. I know you're listening. He's been licensed 32 years. He does a lot of APRS. He's really big into the LoRa, which is something he's been trying to convince me to play with, which I'm definitely interested in. And he does a lot of solar-powered weather stations and that sort of thing, too. So he's an electronics tech for the University of Quebec. Abiti? Abitibi. Oh, man, he's going to kill me. No, actually, he's one of the nicest guys I know, so he probably... and then I call him the embedded programming master because he is the man that has made all this stuff work. The guy's just unbelievable. I can tell you in the past, I can remember sending him a fairly complex idea, and instead of getting back, well, let me see what I can do, 30 minutes later, I get back the code. Here, try this. Did it work? Guy's unbelievable. He really is. And it always worked. There might have been a little bug or whatever, but it worked. Okay, so a little quick history on this. So Remy and I, we've kind of been partnered friends for, geez, I don't know, 10 years maybe now. These are actually two products that he and I did together. The Yag Tracker, which was a graphical APRS display with a built-in modem. That was pretty much it. It was, a graphical display with a modem. It had a pretty nice UI. It wasn't touchscreen. It had a mechanical encoder. And this thing was pretty cool. I ran one as my primary unit in my vehicle for years, and until I decided to kind of shelve it because the main processor is no longer made, and I always feared that one day it would die, and it's like I wanted to archive it. So, and then the other product we came out with was the Ics Tracker, which was essentially a non-display version, if you want to look at it that way. It had a USB interface, and we had some additional things that we had added to it. And it was essentially in direct competition with the Tiny Track and the Open Tracker. So think of it as our version of the Open Tracker or the Tiny Track. So anyways, just wanted to show you that we've been working on this stuff for a long time, various APRS-related products. So let's dive right into some design goals. So here were some things that we said, here's some stuff we would like this to do, whatever this device ends up being. So we got integrated 1200 baud AX25 modem. We wanted it to be USB. FTDI preferred just simply because FTDI driver support is pretty much built in to just about every modern OS now. I know Linux, Windows 10, 11, and so forth. We wanted KISS through USB and Bluetooth, and we'll talk a little more about the Bluetooth aspect of things. We definitely want an integrated GPS receiver. Why hang more stuff off this thing if we don't have to do it? We wanted to avoid going with a specific modem IC, like an MX614, something like that. We wanted to do everything through the DAC and ADC pins, and we definitely wanted to go with something like an op-amp design, which is pretty cheap. We wanted this to operate as an autonomous tracker, but also we want to be able to tether a smart device to it if you want to do more with it. But we want to be able to take that smart device away and have it just kind of take back over as an autonomous device. Small, lightweight, and low cost to produce. And small, lightweight, that was more of a we've had some people say they'd like to, maybe potentially fly this on a balloon, that sort of thing. So that's kind of where we were. But really, low cost is really kind of where this whole thing is based, because when it comes to APRS trackers, it's kind of at the point now where no one wants to spend a ton of money to just have their vehicle showing up on the map. So you kind of have to make it an attractive thing by saying, hey, look, it's not going to cost you too much. I added this minimal LED indication. Now, later in the presentation, you might think that I broke this rule. The debate is it's up for debate. Easy audio adjustment. A lot of the devices are on the market. You either have to go through the web interface or something to actually adjust your audio levels. That's nice and all. But I like being able to just put a small flathead screwdriver on a pot and be able to adjust it really quick. So that was something. And then lastly, a web interface configuration mechanism to be able to configure all your settings. All right, so A lot of choices when it comes to microprocessor. You've got your PICs, your ARMs, your Cortex, that sort of thing. I'm a PIC guy previously. Now, I'm not a programmer. I'm not very good. I've delved into PIC and playing with that. And so it's really fell on what was Remy really comfortable with. And he wrote all the code for those other two devices with ARM and Cortex devices. So I knew he was comfortable with that. What I didn't know at the time when we first started talking about this was he had already started diving into the ESP32. I was starting to dive into that a little bit just out of curiosity. You know, didn't think I could necessarily do anything great with it myself, but I knew with the help of somebody else who could do something great with it. So I think it's safe to say we chose the ESP32. Here's some specs here. I'll just go down these really quick. It's a 32-bit microprocessor. It is 2 CPU cores. It can run from 80 to 240 megahertz. Has 3 hardware UARTs. 12-bit ADC, you can have up to 8 channels of ADC on that. Of course, as you use more channels, of course, you lose more of the GPIO. 2-bit DAC channel, two 8-bit DAC channels. I2C SPI has an SD card interface and PWM. 22 pins of general purpose I/O, so we hang a lot of stuff off this thing. 32 megs of onboard SPI flash, so we don't have to add anything, which we had to do with the Yag Tracker. We had to have an actual separate flash to go with that. I'm sorry, not flash. It was an EEPROM. We want built-in Bluetooth and Wi-Fi. We already talked about that. The Wi-Fi this building, this is good for. It's only 2.4 gigs, not 5 gig, but it's BGNN. Oh, I should mention Bluetooth Low Energy. Now, here's something that I'm not an Apple user. I guess the word is that iPhone devices have to have Bluetooth Low Energy. Is that correct? Can anyone kind of confirm that for me? No? Okay. Because we've been told that iPhone devices typically will not talk to an ESP32 on the standard Bluetooth protocol, but it will on low energy. So that's something I want to get confirmed because, as you can imagine, if you cut out all the iPhone users, it cuts out a lot of your user base. So that's something I want to kind of get to the bottom of. It's 3.3 volt operating voltage, and it can be programmed through the Arduino IDE, but we'll talk about that later on too. There's definitely some things that have to do with that. Okay, so early on, this is what we did to just kind of test, our functionality. Did we have something that could potentially work? So what we did was we grabbed a couple of these. It's the Do It dev kit modules. It's on the left there. You can see it plugged in. And then all I did was I basically just designed a very simple PCB that's essentially just our audio modem section. Didn't worry about any of the other functions. We just want to say, can we get the audio modem part of this working? I did include a TTL UART interface so we could plug a GPS into this thing as we were doing some of our testing. So yeah, that's where we started. Right off the bat, we learned that the decode was pretty good, and we hadn't really even tweaked anything yet. That was the part I was the most worried about, because I've seen with other devices that were trying to do all the software decoding without a modem IC like an MX614. Sometimes the decoding was a little bit dicey, but not with this thing. And remember, this was just a mock-up. So you can see that the module. Whoops, wrong button. Anyways, got the module there, and you can see it end up soldering a whole bunch of wires on this thing. It was kind of hacked up, and we kind of started aiming big, We got one of these touchscreen LCDs, started getting everything all wired up, and this is kind of where we started. So that leads me to, it's time to take a step back. We're probably getting a little ahead of ourselves. We don't even really have complete hardware yet, and we're getting all crazy with LCDs and everything, which feature creep can kill a project. Yeah, go ahead.
Just a question.
Yeah. Oh, yeah, microphone.
Check.
So what was the LCD module that you interfaced with the ESP32?
Okay, the question was, what was the LCD module? That module is, give me a second. I'm trying to remember who we bought this from, because we ended up going through a couple of different vendors. Can I get back to you on that? Because I don't remember the exact module. This was it was a 5-inch TFT with capacitive touch. And that was the other thing too. This module was like $100. And when you're talking about $100 for an LCD, you're not exactly talking about low cost. So again, this was another like, whoa, cool. Oh, actually, hang on a second here. We're kind of getting outside of our design goals here really quick. So anyways, this is still slated for something down the road. We definitely want to do something with this, and the LCDs are getting better and cheaper and everything. So this isn't a dead idea, but I did want to show this because this was kind of our path of, you know, where we were going. Okay, so we said we're going to take a step back. And so we said, let's hold off on that display. That's, you know, we're getting a little crazy here. Let's solidify the packet generation, decoding. Decoding was working pretty well. We're going to talk about the packet transmitting side of things. We need to decide on a form factor. Like, you know, okay, that LCD was going to obviously kind of say, hey, this thing's got to be this big, you know, that's way bigger than what we originally talked about. Let's take this thing into a, you know, cohesive physical design. Let's kind of decide. And then let's stop hacking all this and start designing. And by that, I mean, I'm not real big on bodging wires like that, soldering to the back of a board and stuff. With the cost of PCBs today being so cheap, I'm real big on, let's go ahead and get a board designed. And it's only going to cost us maybe $50 to get, you know, half a dozen boards. Let's just do that. If we got bugs, if we got problems, we'll fix it. It's not like the days, when I first started doing this stuff 20 years ago, 22 years ago, when I was literally in my bedroom in high school, there was no, let's just get a couple test PCBs, because it was going to cost me $500. You know, that wasn't going to happen. I was a high school student. Today, with OSH Park, JLC PCB, some of these others, I mean, you can get 4 or 5 test boards for well under $100. So that's kind of what I mean by that. You know, let's go ahead and dive in. A little self-explanatory, right? So yeah, so we got to that point, and then this happened. Okay, so we said, okay, well, what do we do now? Every day I'd go on Mauser, and I have my BOM, and I go through, and I go, oh, that part's not available now. Okay. Next week, oh, those 2 parts aren't available now. Great. What are we doing here, you know? So, I mean, the thing was on hold for quite a while, so we just kind of stopped. We were working with the parts we had on hand, which wasn't much, and you sure as heck wasn't going to start adding new parts in that you couldn't get, you know? So, all right, so we got past all that. We got all past that. So let's start diving into some of the more technical aspects of this. So here's your ESP32. And this is basically your minimal connections. Let's just ignore this stuff for now, because obviously these are not the minimal connections. But when it comes down to ESP32, you need to tie the enable line high. You need to have some good filtering. Okay, so one of the things we found with the ESP32 is it is a little bit finicky with voltage fluctuation. So you want to filter it pretty well. So here we've got a 0.1 microfarad and a 22 picofarad cap on the main supply pin. That's done wonders for just getting all your transient voltage noise out. But also on the power supply side, we've got a 3.3 volt LDO regulator coming right off the USB port. We've got 10 microfarad cap on the input side, and we got 100 microfarad cap on the output side. And that seems to have really choked off any issues power-wise. That's done a pretty good job, actually. The only other thing is this ESP32_IO0 pin. That's very important because we need that to put this thing into a bootload mode. We're going to talk about that here in a minute. This resistor sometimes is needed and sometimes isn't needed. I know that's about as clear as mud. We included it because it doesn't appear to hurt if it's there, and it acts as a pull-up. But in some documentation tells you don't need it. Some says it does. We went ahead and added it, and it doesn't appear to hurt anything to have it there. So that's your basic connections just to get this thing powered up. Okay, so let's talk about the flashing. So the ESP32 is really nice the way it works as far as flashing it and resetting it. You can do all this through those pins. But there is a little bit of, I call it the the pulsing dance, the way that the pins have to be pulsed and timed to get this thing into bootload mode. What we found was, so this is kind of the traditional reset circuit that a lot of people will spell out. I think even the ESP32 documentation spells this out. This works most of the time, but it can be a little bit finicky. It doesn't always work. What we did find is we found this IC right here, which is essentially this in a single package. This thing is rock solid. We never have had a problem with it. So we end up going away from the discrete component and going to this. Now, what's really happening here is that by pulsing the DTR and RTS lines, you're getting, so you know, like when this goes high, this is tying this through, but it's also tying back through to here, and it back feeds through here. And by doing that, it's pulsing the pins correctly. Now, in order to get these signals, you can either have a true RS-232 serial port, which who here still has a computer? Let's say a laptop that's got an RS-232. I know most of us have a desktop, you know. So obviously the FTDI was the way we wanted to go, and the FTDI is one of the few commercial options out there that has DTR, RTS, you know, these lines to be able to do this function. So we originally started with the FT232, which is kind of the more popular version. However, that thing is virtually impossible to get your hands on right now. It's still part of that part shortage. And it's about an $8 or $9 part. Well, FTDI came out with the FT231X. This thing's only like $1.50 or $2.10, something like that. Way cheaper. And it does all the same functionality, and you can buy these right now. I can go on Mauser right now and actually go buy one of these. So we decided to move to that. Still have the functionality that we needed. So this is your basic, you know, as far as the interfacing to this IC, you know, your USB connector. We're still doing some power filtering here as well, just power filtering before you're getting to the regulator, to the LDO regulator. And then our RTS DTR line, then of course our transmit receive lines. So that's generally been a very solid circuit. Once we came up with this and kind of eliminated a few problematic things, this has been very solid. And I'm here to tell you, I spent a good probably 2 weeks troubleshooting why I couldn't get the ESP32 to go into bootload mode. Sometimes it would, sometimes it wouldn't. It was extremely frustrating. And I thought to myself, well, if this becomes a product and we start shipping these, no one's going to put up with that. You know? So I was like, we got to get this thing working perfectly every time. So I just threw this up here. This is the pulse table or truth table for those pins. So you know, you can see, you know, if DTR and RTS is high, then that gives you a high on the enable and the IO0 line and so forth. So if you're interested in truth tables, if that's like your thing, there you go. I did that just for you. Okay, and real quick, this is just just showing where those, and now I don't have a timeline here to show you the actual time, but basically what really is happening is VCC's got to go high first. Then the RTS line has to go and stay high, and then the DTR line has to pulse. But they can't all come up at the same time. They all do it in succession. Okay, so let's dive into the audio of the op amp. So it's a dual op amp setup. We've got the transmit path and our receive path here. Okay, now pay attention real quick to this right here. Okay, that's going to be important later on another slide. So just remember that, because a lot of people look at that and they go, well, why are these tied together? I had to ask that question. I said, hey, Remy, well, why are these tied together? He goes, let me explain. Actually, he's really good about hand drawing stuff, and then he'll take a picture of it and send it to me. And I'm looking at it going, oh, okay. So, and in fact, I took that hand drawing and I tried to make it nice and pretty for a slide. So we'll get to that. But anyways, the transmit side of things, basically you're going through the op amp, and then we've got a low pass filter here that is filtering, and then we've got a 10K trim pi here to control our level, and then of course we're going through a 0.1 microfarad cap. Now, I'll just go and caveat this by telling you right now that we're having some transmit audio problems. Now, I've got some scope shots I'll show you here in a couple slides, and we're not exactly sure what's wrong. Now, here's the really frustrating part. Remy's got a hand-built perf board version of this that works perfectly. He didn't have a single problem with it. I've got a beautiful surface mount PCB, and I have all kinds of problems. One working theory is that with all the jumper wires and everything, maybe the impedance, it's really hard to say. So I'll just go ahead and say now, if anyone's got any ideas, I'm open. I'm open to any ideas because I'm running out of ideas of what could possibly be wrong. Now, so we'll table that for a second, okay? So on the receive side, very simple. We're just running it through the op amp, and then this is a feedback. This trimmer acts as a feedback to act as a feedback for that op amp section. One thing we found is that 180K resistor was just way too high, so we replaced it with a 27 because I was looking at this thing and my audio level was so low, and I said, "There's something wrong here." And Remy goes, "You know what?" He goes, "That might be a little high. Let's try it." So we threw a 27K in there. Audio went way up. If you've ever worked with commercial radios, Motorola, any commercial, they want a lot of audio. So I was testing with a Motorola CDM 1250, and I could barely get any transmitted audio passing through, and that was with the emphasis, and the emphasis turned off, all that stuff. So swapping out that resistor made a big difference. Okay, so I got a couple little flow charts here just for those of you who are really into this. This is the kind of stuff that Remy hand drew out and sent to me. He goes, here's generally how it works. Because again, I'm a hardware guy. I'm not really a software guy. So, but basically, he's generating the tones out of the DAC. He's going through an I2S bus at 50 kilohertz sampling. The tones are being generated, then it's going through the DAC, and then the audio is coming out. And then, of course, that's being passed through that low-pass filter that I showed you in that schematic. And, of course, that's going through a 10K ohm trim pot to control the level. Okay, here's where I really kind of get off the bus. And I'm just going to be honest with you. So if you have any questions about this stuff, I will be more than happy to write those questions down and go to Remy and maybe get some more meaningful answers for you. But the decoding, the way that he explained it to me anyways, is basically he's taking that post bandpass filter audio, he's running it through these mixing sections essentially, but he's of course doing all this in software. And he's running against a sine wave at 1200, cosine 1200, sine 2200, and cosine 2200. And then he's comparing it down, and then he gets a bit at the end. Is it a 1 or a 0? And then the correlator 2, he's doing a much more simplified version. But these are the two correlators he's using to run all this audio through. And again, I'm not going to stand up here and pretend to understand exactly what he's doing here, okay? Those correlators are part of this now. So you got that AFSK audio coming in. It's going to the, whoops, keep hitting the wrong button. Sorry about that. Going through the ADC, it's going through this I2S bus, and then he's running it through some bandpass filters, and then he's running that through those two correlators. So he's doing this for the 1200 and 2200 hertz, running through those correlators, and essentially what he gets at the end is he has 4 different decoders. And what we found is when we run the audio through all 4 of these decoders, most of them decode every packet. Decoder 3 and 4 tend to be the ones that are a little bit more picky. But I did a test about 2 weeks ago. I just set this thing up in my shop, and I just let it run on the air with a radio. I came back a couple of days later. I had right at about 4,800 packets that had passed through this thing, and decoder 1 missed 1. It missed 1 packet. Decoder 2, I think, missed 3. And then things started to dive off, and decoder 3 lost like 500 packets, and decoder 4 lost like 800 packets. But that's pretty good. I mean, for a 1200 baud channel, we all know how finicky 1200 baud over an FM channel can be. So I thought that was pretty good, especially for decoder 1 and 2 to only miss 1 or miss 3. Okay, so remember we talked about that line that was going from one op amp to the other. That's where this comes in. So what Remy was explaining to me was when it comes to the ADC range, is that if the audio drops below that 0 level, then it's the equivalent of I don't know what the best way to describe it. It's basically, it's out of the range. It's out of range. You can't deal with it. So by having that wire going from, or that path from the one op amp to the other, it allows this thing to basically auto adjust. Okay. So the example we have down here. So the example here was, okay, it's out of range. By that auto adjust, we're just using an example of 100 millivolts here, and but what it did is it essentially pushes the audio up within the ADC range, 0 to 4096, and it allows him to be able to decode the packet, or at least to decode that particular part of the packet, and that's where that tying those two op amps together is very important, and I believe. Based on what he was explaining to me, that's a reason why we are getting such a good decode rate, whereas other TNCs probably, or other modems I should say, is just going to toss that out because it's outside of the range. It's like, I can't deal with it, and it just tosses it. So that's why that was so important, and that's why we're getting such a good decode rate. All right, so we did have an interesting bug that Remy was using an older oscilloscope and he didn't see it, but when I ran it through my storage scope, we saw this. I said, well, that's kind of interesting. That doesn't look right. And realized we had some bits that were swapping. As you can tell, you can see how the audio is actually going up, then it's dropping down, going up, and it's consistent, you know. And then, of course, it reverses. So this is just an example of how a very simple bit shift can cause something like this. And Remy didn't see it because his older scope was rounding all this off. He was like, oh, I never would have seen that, and I just happened to run it through there. So I just threw that in just to show you these are the kinds of little things that, you know, will creep up that you might thought everything was fine. The interesting thing is he was transmitting his audio through his handmade board using this, and it was decoding. It was getting decoded. So, but my stuff, it was like, nah. This is the raw audio. So this first trace here, that is the audio straight out of the pin of the ESP32 before it hits anything. Okay, this is coming out of the op amp just before the low pass filter, and this is just after the low pass filter. Okay, so this is no radio involved here. This is just straight audio going through the path. This is 1200 hertz Fsk test waveform over the air. Okay, so this is sending a 1200 hertz tone over the air, and this I am looking at the 9600 baud, basically the discriminator pin of a receiver going straight into my scope. So you can see it's fairly clean. We do have a little bit of this here, and that could potentially have something to do with why it's not being decoded. The jury's still out. We're still working on it. This is the 22 hertz version of that. So I kind of threw these in just to show that's how clean it is going into the radio. Okay, and this is what it looks like. Now this is with pre-emphasis and de-emphasis technically on, and the reason I say that is I can turn that off in those Motorola radios I was testing with, but most of your amateur grade gear out there you can't turn off the pre-emphasis and de-emphasis. So we decided to go ahead and start testing strictly with those radios instead of the commercial, because I want real world results here. You know, is this going to work? If I give you this and you plug it into your IC2AT, you know, handheld from what, 23 years ago, 24 years ago, is it going to work? You know, so that's really what it comes down to is, can I hand this to you and can you plug? Because, you know, we're always telling you, hey, if you want to get on APRS, you got an extra 2-meter radio hanging around, you know, a handheld, mobile, whatever, it's 20 years old, you know. Now you got use for it, you know. So that's kind of, you know, the purpose here. Is it really that? Jeez. Okay. Yeah. Okay. Yeah, that was the one with the thumb wheels, right? Yeah. Okay. Yeah. No, I wasn't even close. Samsonite. Anyone get that joke? No? Okay. All right. I was way off. My wife will get that. She'll watch this later and she'll laugh. And then she'll call me a dork. So this is the GPS we decide to go with. And this is the most expensive part. okay? But I think it's worth it. But I'll give you a quick little anecdotal story. When I was 14, 15, I went to a ham fest and I paid $120 for a used Garmin GPS 38, used, just so I could have a GPS. I paid $120 used. This is $16 in single quantity. I think that's pretty good, you know. And of course, you start buying in more than single quantity, price does go down. So anyways, it's a 22-channel GNSS receiver. They don't really call them GPS anymore. They've gone to the global navigation satellite system. It's tiny. It's only 9 millimeters by 9 millimeters, so it's a tiny little package, so we can squeeze it in there. 3.3 volt, that's always nice, keep everything the same. This thing tracking is only drawing 28 milliamps when tracking. I think I meant to put it up there and I left it out, but I think when it's trying to first get lock, I think it goes up to like 36 milliamps. So, geez, you know, this power budget's killing us, you know. Excellent out of band rejection. That's the other thing about this. You know, I look at the spec sheets for some other similar GPS receivers, and they don't give you any information about out of band rejection, but this particular company, they give you a lot of information about it. Really good. And that's proven too, because I have several of these running on my bench in my shop right now. The antenna's just laying on the bench around a lot of other stuff that's going on in my shop, and it's tracking just fine. TTL serial NMEA output, 0183 output, NMEA output. So of course that's compatible with about everything we're doing. Baud rate on this thing is really easy to set. You either ground 2 pins, ground 1 pin. You know, it's only just 2 pins to set your baud rate. The 1 pulse per second output is actually programmable. It's one second by default, but you can make this thing do a lot of different speeds. That's important, and the reason I put that in there is because one of the things I really would like to see doing with this is do time slotting. And if you're not familiar with time slotting, essentially what you can do is you can take a whole bunch of trackers, put them on a single channel, and you can you can time slot them so that way, you know, at the top of the minute, you know, this one transmits 5 seconds later, this one transmits, and by giving them time slots, you can get a whole bunch of trackers into a single channel in a minute's time. And it's really handy for things like, you know, a bike race or something where you're trying to track a whole bunch of assets. And of course, it's got a 3-volt battery backup, so I gotta get going here. There's the circuit for the GPS. Nothing real special. Let's see, anything special I want to point out here. It does have a fix pin, which is nice. It goes high when it's got a fix. So if you just want a simple LED indication that the GPS has a fix, I don't even have to, you know, have the ESP do that. I can just, and that's one of the LEDs that we're using on the board to just give us a quick indication, does this thing have a fix? Radio interface, we went with the mini DIN. We could have gone the DB9 Cantronics, but the mini DIN is pretty much the standard now, and makes it sure makes it easy. When you got a radio, it's already got a mini DIN port on it. You take a mini DIN, the mini DIN cable, plug and play. Okay, so this is the current hardware. And if anyone wants to get a closer look at this, I got a couple of these set up in the demo room if you want to come take a look at this. The only thing missing off this board right this second is the mini DIN connector. But anyways, you can take a look. This is the hardware we've got, and you can see my fingers, and it kind of gives you an idea how big this board is. There's a much better picture that I took in my little light booth, so you can see it a little bit better. We have made some changes. We revised the trim pot. That trim pot there, these are almost impossible to get now, of course. So we went to a slightly different one. We did I added a voltage divider on the voltage coming in off the USB port, so we can now report that voltage in the packet. We added this analog MCP 9701 temp sensor. You might think, what's the point? That's kind of nice. If you have the thing in a hot car or whatever, and you have it reporting at any given time, you can go look at it and say, oh, okay, it's 135,000 degrees inside my car right now. It's kind of nice. And actually, that's an homage to Scott Miller, because Scott Miller was one of the first people I remember putting a temp sensor on the tracker board, on the open tracker, and I used to use that function all the time. Living in Virginia in the summer, it gets a little warm. We've added some LEDs. We've got power, which we already had, transmit receive, which is bicolor LED, which I didn't point out real quick, I'll point out. This LED right here is actually a bicolor LED. It's red and green. There's your GPS, and there's your power LED. Why did I put them here? Because it was convenient, okay, and I was lazy. But anyways, we've added LEDs for also Bluetooth status and Wi-Fi status. And the mini DIN, we went to a more narrow profile connector. So here's what the hardware will look like. I just revised this maybe about 5 days ago. There's all your LEDs now. Everything's lined up nicely. Got your temp sensor here. And then the pots are a little bit bigger. So that's your improved hardware, and that's essentially what it's going to be when it's all said and done. Configuration, you got a couple options right now. There's a command line, kind of like a DOS, but then Remy built in a really cool text editor right into the tracker. So if you're in it with PuTTY, you just go to the text editor, and it looks much like almost like a batch file. And you just go in there and, TNC, the call sign, GP, and there's a whole bunch more settings. This is just an example. So I just threw that in. Eventually would like to go to the web interface. This is just something I mocked up in HTML really quick just so I had something to show. It may or may not look something like this, but that's the goal. I mentioned Arduino IDE. It's a piece of junk. I'm just going to say it. About 2 weeks ago, Remy said, hey, by the way, did I tell you I moved over to VS Code and Platform IO? And I was like, no, you didn't tell me that. I was like, so I guess that's what we're going to do. So that's what we're doing now. We've moved over to VS Code, Platform IO, and I just threw up here. These are the 3 things that have to be installed to make this work: VS Code, Visual Studio Code, Python, and Platform IO. And as soon as I get back to Virginia, I'm going to set this all up, and the way I can start. Okay, we talked about tethering with smart devices. These are just some quick screenshots from my phone. This is you can see I'm tethered to the ESP-TNC01. This was transmit attempts. Here's some receive packets that came in. Of course, just some stations and some mapping. So, and the cool thing about this is that I can do all this, and then when I'm done, I just turn off APRS Droid, and tracker goes right back into autonomous tracking mode. So let's talk about cost real quick, because I'm sure everyone's curious. ESP32, these are all current pricing I pulled yesterday, okay? ESP, $4.08. Remember, this is single quantity pricing, so if we get the quantity up, prices go down. The GPS, $16.80, the FTDI, okay, I was a little off. I think I said it was like $2.05, $2.35. The temp sensor, 58 cents. Mini DIN connector, $2.50. All other parts on that board are under 50 cents a piece, or most of them are under 10, like all your passives and everything. Those are all well under 10 cents. So about 40 bucks, that's not bad. And that's in single quantity. If you were to go out and buy all these parts and try to build one of these. So questions? Any questions? Sorry, I started kind of rushing through the end because I was running out of time.
If you're building something new, I think it is long.
Yeah.
No, it wasn't on. Okay, it is long past time to junk 1200 baud AFSK. Please do not build a new system that uses it. In Southern California, San Diego,
I guess my whole point being here today was pointless. I'll pack up and go home.
No. The rest of your stuff is fine. Okay, it's just the RF modem. Okay.
Okay. So
let me finish my point.
Okay. Yeah.
In San Diego, we have been recovering National Weather Service radio signs, Vicella RS-41s. Okay, they have a 50 milliwatt transmitter. We can easily reprogram with firmware that's coming out of Europe and out of Australia, out of Adelaide, with 4 FSK at 100 baud with coding. The RF link margin is at least 20 dB better. 20 decibels. Okay, do you know how much 20? That's 100 times
I get it.
power.
Yeah.
All right.
Yeah, I
Look,
get it.
if you don't believe it, I will gladly send you
I believe you.
one.
I believe you.
I will gladly send you one. Okay, they weigh 85 grams with the batteries. They're essentially free. We pick them up off the desert. Okay.
Well, somebody paid for them.
Now you could implement the same thing or something very similar.
Yeah.
It would actually be much easier for you.
Yeah.
Much easier. This data rate is so low. You can take one of these Silicon Lab synthesizers and reprogram it through the I2C bus at 100 baud easily. That's what we do. Okay. And as I said, you can get over 20 dB better link margin. I mean, that is enormous. Please do not use a modem that was obsolete when it was chosen in the early 80s because Bell 202 modems were readily available, okay?
Well, I mean, I get what you're saying, Phil. I really do.
The rest of your design is fine, just the modem.
No, I get what you're saying. I guess we look at the APRS network of what's currently out there. You know, what's it compatible? And I mean, what you're describing is not compatible with the current network, correct?
We had exactly the same concern on the other guys. Once we discovered how much better this worked, we realized we didn't need the network.
Yeah.
Because we can hear it directly.
Yeah.
20 dB means
Okay.
I don't care about the existing network.
Okay.
Because I don't need it anymore.
Okay. One caveat I will say is, you know, I mentioned that Remy's into LoRa. And one thought was to maybe integrate LoRa into this. You know, we could, you know, make a LoRa version of this. You know, I mean, we haven't produced anything other than prototypes yet. You know, I own every single prototype right now. I got, you know. So, anyways, I appreciate your input. You know, but I will send you one. Okay.
Do we have any more questions?
Yeah.
Okay, hold on.
Okay.
I'll get back to you. Hold on.
Oh, you started out your presentation with a nice touchscreen display, but if you've got Bluetooth links into phones, do you even need that?
Well, okay, so that's a very good point, and that's kind of that. I guess I kind of left that out, and that's a very good point. That having that ability with the phone or a tablet or whatever does kind of eliminate that. There are some people that do like that tactile. Or not, that's the wrong word, actually. They like having that all-in-one device that they can just put in their vehicle, like, you know, a D710G or whatever. So I guess in a way we thought, oh, maybe it would be nice to eventually have that all-in-one device. You just plug power and a radio into, you know, and then you would have that. But yes, you bring up a very good point, and that's one of the reasons I love the whole idea about being able to connect a smart device. So, yeah.
Have you given any thought to support for any other sensors besides temperature, things like barometric pressure and particulate count?
Yeah, so actually, the boards are going to be literally sitting on my doorstep when they get home. I got a test board I just laid out for a BME 280. It's a Bosch sensor that does temperature, pressure, and humidity. And it's I squared C or SPI, I forget now. We were talking about maybe trying to do a version of this that would have more sensor input, maybe some GPIO that's brought out for being able to do a weather station, something like that. Because my wife's a meteorologist for NOAA, so it's definitely an interest that she has, which kind of falls on me as an interest as well. So I definitely would like to do something like that. So yeah.
And I'm afraid we're out of time.
Okay, yeah.
Thank you very much.
I appreciate it.
Thank you, Jason. Yeah, I'll leave that up there.
And Jonathan, come on. Which one of them? Oh, I see. There's two on here. Okay. And you're about 20 minutes. Okay. And let me give you this microphone. Okay, next up we've got Jonathan Rizzo, KC3 EEY, amateur communications below 9 kilohertz.
Hi, I am Hi, my name is Jonathan Rizzo, KC3EEY. I'm a VLF natural radio enthusiast and also an electrical engineer. This is a topic and interest that I have been recently introduced to over the years, and this is something that is very new and exciting for me. Again, if you would like this background information, please see me. So I would like to introduce to you the Dreamers band. This is below 9 kilohertz. Experimenters have utilized the lower VLF band and ULF band to send messages for years. Recent experiments in the early 2000s have led to what is referred to as the Dreamers band. The Dreamers band refers to frequencies below 9 kHz. The VLF and ULF band presents some unique but rewarding challenges due to inefficient antennas and noise from spherics. Those are the radio emissions from lightning discharges. Recent experiments by Marcus Vester, DF6NM, Dex McIntyre, W4DEX, Bernd, DL3, JMM, and many others, as well as software by Paul Nicholson, made it possible for VLF amateur communications in the Dreamers band. Propagation through the Earth ionosphere waveguide, and the boundaries for this are the ground and sea and the D&E layers of the ionosphere. Propagation paths are phase stable. They are low loss, 0.5 to 8 dB per 1,000 km. And that loss varies depending on frequency, time of day, land or sea path, and direction relative to Earth's magnetic field, and that's also very important. Practical size antennas do not radiate effectively due to their fractional wavelength. It can be expected that a small VLF antenna can only radiate 5 to 20 microwatts, and I'm referring to a kite antenna or a balloon antenna, and up to a few milliwatts or with larger kite and earth probe antennas. Reception techniques that reduce local interference and offer powerful signal processing on modern PCs and narrow bandwidths with GPS timing open up the band for use. So there are two modes. There is coherent carrier mode. A CW carrier can convey 1 bit of information using narrow but a coherent CW carrier is an effective amateur communication in the VLF band. The carrier is locked to a frequency or timing reference, usually GPS, but you can use a cesium or rubidium reference as well. At the receiving end, the signal is often too weak to be detected directly, so long integration times are required. In many noisy environments or frequencies close to the Earth ionosphere waveguide cutoff, that's around 1.7 kHz, integration times of 12 hours or longer are often necessary. The EBNOT digital mode, this mode was conceived by Paul Nicholson. It uses coherent BPSK modulation for message encoding. Frequency and phase coherence is provided by a frequency or timing reference. It utilizes very strong forward error correction that requires the processing power of a modern PC. It uses 6-bit character codes. There are 52 character codes, and this gives a 5.7 bits per character information capacity. It implements CRC16 error correction and convolutional codes using long constraint lengths, which can yield successful results at EBNOTs of as low as 0.5 dB. The bit rate is extremely slow, often on the order of bits per hour. This is also pretty interesting. This is the first amateur mode that requires more power to decode the message than it does to transmit the message. So for a basic EBNOT setup, the coherent, a coherent frequency source locked to a timing or frequency reference for carrier generation. That could be some sort of signal generator that is locked to some sort of reference. You need an audio transformer with a switching circuit. You could use a relay or a transistor or IC to switch the polarity of the carrier across the audio transformer input to perform keying. So on the output, you will see if you switch the polarity on the output, you will have an inverted phase. Keying is performed by changing the polarity of the carrier signal across the audio transformer input. The output will be 180 degrees out of phase when the polarity is reversed as seen from the audio transformer input. The message is encoded with EBNOT and then provided to EBKey. Those are the two programs that you would use, which would either key a serial port, control lines or GPIO pins that keys by toggling the carrier polarity. This mode can be done at LF, but a balanced modulator circuit must be used as relays are too noisy. So the programs that I was talking about, EBNOT is the encoder and decoder program. It is available as a precompiled binary for Windows and also source code for Linux. It accepts messages directly via pipe for encoding and baseband modulation for decoding. EBKey, the keyer program, accepts an encoded message from EBNOT and controls either two serial port control lines or GPIO pins to key the message. The serial port or GPIO pins then connect to the relay that will switch the carrier polarity at the audio isolation transformer input for each bit that's modulated. For a much cleaner, simpler, and often cheaper method, you could use the program EBSynth. It's an all-in-one coherent frequency synthesizer and modulator utilizing your sound card. It accepts a GPS pulse per second signal or 19.531 kHz reference, and that's divided down from a 10 megahertz reference for coherent carrier generation and bit encoding. It accepts an EBNOT encoded message via pipe, and it has multiple output options, and it can also perform carrier generation for carrier transmission. This is the EBNOT main display. This can be run on a PC or a Raspberry Pi, but it must be run on Linux because it requires ALSA. Another important note is that the sound card must use the same clock for audio capture and playback. And this is due to the internal loops inside the program. If it uses separate clocks, it will lose sync. So most normal sound cards do have one clock, but the cheaper USB sound cards often use a clock for playback and a different clock for recording. This is an example of an EBSynth rig using a Raspberry Pi 3 and an audio injector stereo sound card. You can see the GPS module outputs a pulse per second signal, and that goes into the left channel of the input of the sound card. There's a feedback line, which is necessary if you use the pulse per second option to maintain those internal loops. Normally, you would get the feedback signal from your antenna, which is often picked up by a probe or a loop. The output is available on the left and right channels. There is an option for an I and Q output. If you have orthogonal loops, you can feed I and Q to both of those loops. You log into it and control it via LAN and ensure that the time is set that the time is set by NTP at least. This is another example of a rig using a Pi 3 and an audio injector octo. This has 4 inputs, but this is just an example. So for audio power amps, it is often convenient to use an audio power amp as a final stage before the antenna. Care must be taken to match the antenna impedance with the output impedance of your audio amp. Radiated power at the antenna will always be much less than the power output from your audio amp. Even the largest of practical VLF antennas will only ever output a few milliwatts. If taking the feedback signal from the PA output for EBsynth, ensure that mains, hum, and harmonics are reduced as much as possible. A popular antenna option are earth probe antennas. Using the earth to radiate signals has been done for many years and can be an effective way to create a very large loop antenna in a practical way. Kite and balloon antennas require lots of wire and are not permanent. VLF amateurs have had great success with both carrier transmissions as well as EBNOT messages using earth probe antennas. Earth probe antennas are very simple to construct. Simply insert 2 metal rods in the ground. The greater the distance, the larger the loop. Soil conditions can affect the radiation resistance. And be sure to take an impedance measurement and match it to your PA. This is an example of an earth probe antenna. It's just a simple ground rod with a clamp and a antenna lead. This is as simple as it gets. However, you need to make sure to match impedance for effective radiation. So here are an example of EBsynth setups, rigs that other people built. Marcus, this is his rig. He uses a Raspberry Pi Octo. That is his EBsynth display. He also uses a current meter to measure antenna current. He has a feedback probe from the antenna and a power amp with a fan to cool it. He has a wire antenna, so he uses this loading coil that he built using 2 garbage cans. This is Domenico's setup, and he uses an old PC with an Intel HDA sound card. So it's very easy to get started as long as your sound card uses the same clock for recording and playback. This is Burns' setup. He uses a Raspberry Pi and an audio injector 0. You can see his GPS receiver in the smaller enclosure. He has had very successful transmissions. And for wire antennas, for probe antennas, you can see that the loading coils do get quite large. These are 2 loading coils made from these large drums. It is a lot of wire, but they are very effective. These were from some of the original experiments. Sir, wait till after the talk, please. Thank you. Real-time communication is not possible with carrier or EBNOT transmissions due to low power levels and a slow transmission rate. A VLF amateur announces his transmission to an audience of VLF amateurs via an internet group or to his friends. A VLF receiver will be installed and constantly recording the spectrum to a data store. Data is pulled from the data store for the transmission duration and saved to a file for processing. The file is sent through a signal processing chain to apply main sum filtering, bandpass filtering, spheric blanking, and either decoding in integration with EBNOT or narrow bandwidth integration with CW. The best reception locations are usually rural areas where mains hum can be easily filtered. VLF receiver with GPS timestamping and resampling is required for coherent reception. A harmonic of the PPS signal is 8720 kilohertz. Crosstalk from the PPS line into the VLF audio line into the sound card can result in a false detection of a carrier at that frequency. Bearing of incoming signal can be determined using triple axis reception. After the file is pulled from the data store, it is filtered using a mains hum tracking filter. What it does, it will track the mains hum and its harmonics and adjust as that frequency varies over the day. The spectrum is then filtered with a 3 kilohertz wide bandpass filter. Then that spectrum is then passed through a spheric blanker. It takes an initial measurement of the noise floor and then uses that value to attenuate spherics. And it can be set for day or nighttime spheric conditions. After blanking, it is multiplied by an LO to produce a complex baseband signal. The baseband signal is downsampled to around 100 hertz, then is fed into the decoder. And for carrier detection, that signal is sent to a narrowband spectrum analyzer for integration. Here is a carrier mode. Here is a quick example of carrier mode operations. You can see the peak here. This was from Germany to France. This was from France to the UK. And you can see the peak. This was 14 hours of integration. This is a stacked decode where the transmission was sent 3 times and stacked for a 10-character message. This is the first ever SID observation with an amateur transmission. You can see it at around 11 UTC. And this is a transmission that occurred yesterday from Bern, and there was also a SID at that time. And this is the decode from his transmission, and you can see the message at the bottom of the screen. And here are some resources and links if you need them. Thank you very much.
And do we have any questions? Raise a hands. Oh, that's right. Sorry.
pardon me for these basic questions, but you, on those barrels, you had 4 loops. It looked like 4 separate loops. If that's the case, what were they for? And if you don't mind, what is SID?
So those loops make up the loading coil of the VLF antenna. So obviously, I did not build them, so I don't know, but I do believe that they did not have wire long enough to cover that, so they're probably separate. And SID is a sudden ionospheric disturbance, and that occurs when a solar flare ionizes the D layer.
Question here.
Yes.
Yeah. On those coils, approximately how many meters or feet of wire are on each one of those coils?
I unfortunately cannot answer that because I didn't build them, but those look like 55-gallon drums, so you can make an estimation.
Well, thank you very much. We're out of time. Big round of applause for. Thank you. Thank you, Jonathan. Very exciting project. Okay, so we're going to move into a break, and we'll start our next talk at 11:15. So be back before then so we can start on time. And I forgot to mention at 11 a.m. is the introduction to high definition ATV down the hall with Mel Witten. So if you're interested in introduction to high definition ATV, proceed on down to the end of the hall, take a right.
Good. Excellent. Okay, got it. Thank you. Thank you, thank you.
took the cap card out of my camera, I was listening to it on the laptop. So I was just physically hearing it over the drive. But he can control, but he's sitting. Yes. Right. I didn't look at, there's a level on my camera, and it looks the same as the difference is fine. So I can't. Yeah, but I mean, just like, I don't know, that wireless pack I used to have. So.
You know, I was wondering how you blended the, because the light on the subject is so much less than the slides. I was wondering how you,
It's just because the projector's so bright.
yeah, that's what I mean.
Yeah.
So we video the screen and record the screen directly, and he focuses
Yeah.
with a good camera on you, so he can track you. You're moving the screen.
Excellent. Yeah, that's great. Good setup. Good idea. Is he doing the switching too?
No, I'm doing the video switching.
Ah,
So I've got this computer, I'm monitoring the YouTube stream when it's live.
okay.
This computer gives me a computer control surface to this, so I can either use push buttons or click.
Mm-hmm.
And so this is the magic video box.
Ah, okay.
And this, if you peek around,
Yeah, I saw.
is this gives
16?
me this gives me each of the cameras.
Oh, yeah.
My on break slide, which is what we're currently sending to YouTube.
Ah.
And
What does clean feed mean?
it's like program, but I'm not sure what the difference is. But
I was just curious.
Yeah.
as long as I don't see a difference, I'm happy.
A lot of stuff here. Thank you for bringing all of it.
Plugged in. I got a 14-foot trailer.
Oh, my Lord.
Fortunately, your laptop came with a built-in LPS. This is hot water to run through the steps. Okay.
Yeah, the laptop's got a pretty good battery. So I was running just on there.
Okay, testing 1, 2, 3, 4, 5. Hitting it hard 1, 2, 3, 4, about mid scale on my transmitter. And testing 1, 2, 3, 4, 5.
Test 1, 2. 1, 2. Ah, got it.
Testing 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Oh, okay.
I think it's just that mic is that handheld mic is hot because he sounds okay with the left mic, and when people hold that mic too close, I think it's just.
And of course, their mic is tipped forward just
Yeah,
a bit.
yeah, sure.
That gives that gives a better view for the
Got it.
camera. Because when we had some shorter women presenting yesterday, their heads were like only half involved. So I,
Need a box for here.
sorry?
Need a box.
For us to trip on
Yeah.
and fall off.
You're mic'd up. Are you ready?
Yep.
Okay, Jason. Okay, let's go ahead. We'll have to stop the conversations. Hello? Hello? Please. Are we ready, George? Okay, thank you very much. All right, welcome back, everybody. And for our next talk, I would like to introduce David Vine, WA1EAW, and his talk, Bushwhacking in the Land of Digital Voice.
It's a very dramatic title, and I think you'll see what I mean in a few slides. So, who am I? Well, I like to call myself an eclectic entrepreneur. My life has been in communications in one form or another. And when I say communications, I don't mean the technical end of it. I mean the actual information transfer. I think it'll be pretty obvious when we go along. I am curious about a wide range of subjects. Like, for instance, my stupid question about sudden ionospheric disturbances. I had no idea that they were correlated to VLF. I didn't know that. And maybe I wasn't listening close enough, but I just didn't pick that up. Now, why am I here? I'm here because I want to learn some of those technical things that I don't know. All right? But as a career communicator, starting as a photojournalist, a writer, author, consultant, publisher, trainer, you know, I'm naturally curious about things. And when I started getting into digital nets, you know, I was introduced to an Echo link. You know, they said, oh, well, go on, you know, do drop in. There's a lot of nets on that. Well, we'll see in a little bit that that's a very, very inadequate direction. Just to finish up here, my experience really literally spans from linotype to terabyte and beyond. For those of you who don't know what a linotype is, it's when they used to use hot metal to make type, hot lead to make type. So it really does span quite a period. And I've been self-employed, you know, up until 2015 when I decided to do whatever I wanted to do. And I'm a 3-time member of the Amateur Radio Service. Okay, this is my proposition. Amateur radio nets are, I would even take that word out and say vital, okay? Because digital voice nets are vital, beyond the radio horizon, mostly reliable, and it is a link for human communication. I mean, somebody who's, you know, experienced with online chat and, you know, social media back and forth, Twitter, they might say, well, yeah, but I can do all that. I want to be able to tune in to a live discussion that I can take part in if I want to. And generally speaking, every single net is like that. DV nets are, well, pardon me for the abbreviation, but DV, I'm going to be using that term. It doesn't refer to me. It refers to nets. Digital voice nets are means of personal satisfaction as well as fulfillment of the basis and purpose of amateur radio. I learn a lot. That's why I'm interested in topical nets, not just some people checking in once a day or once a week. But here's the key thing. Amateur radio digital voice is, I don't want to say an afterthought in company like this, but it really, you know, HF nets, VHF nets, everybody's familiar with those. But due to a variety of factors, they're relatively unknown. You know, I mean, somebody might say, okay, I have this local CSRA TG258 talk group, and why don't you tune in on Saturdays on Echolink, you know, fine. But there is great potential for DV nets to flourish given the proper visibility, bringing them to the public's, or to the amateur radio community's attention. Now, what is a net? Is it just gather around the campfire and, you know, everybody checks in and makes like a 5-second comment or something? No, it really is significant. Nets are, in general, are very significant, both amateur radio via RF and via digital voice. So it's a natural rally point during emergencies. Not necessarily with digital voice, but I will say that the National Hurricane Center and I guess some, what is it, the Weather Net, something like that, they have a channel, and that's pretty well known within that community, that there's, you know, Echolink voice as well as other means of communication. And for current and historical purposes, yes, I know, every night, you know, my net's on the HF side. Is there any traffic for the net? You know, do we have any traffic for the regional? Oh, okay, we'll move on. Do we have any announcements for the net? Nope. We'll move on. Check-ins. So even though, you know, it's just something we do, it is really part of the glue that holds amateur radio together. You know, there are many parts of the amalgam that holds amateur radio together. There's the ARRL, there are local clubs, there's the, you know, the ARRL structure. There's a lot of different things, and now there's YouTube. You know, I mean, it's very visible on YouTube. And, you know, I don't have to say it, but it was a valuable social activity early in the pandemic. It's also a kind of show of force in the sense that in the political arena, you know, if nobody was talking on a daily basis, I mean, they do report the net statistics. Okay, we had, you know, 55 check-ins on this day, and we had 78 on this day. ARRL had this many check-ins on Sunday. So it is part of the total picture when it comes to political force that we have. And it's sometimes educational and often entertaining. Now, quite frankly, I am just totally overwhelmed with digital. I mean, honestly, I don't know why there's so many. I'm not saying there shouldn't be, but I honestly don't know why there are so many different kinds. I guess it's, you know, somebody wants to experiment with different kinds of formats. And so some of them become very, you know, WSJTX, FT8, those, you know, those are household names, so to speak, in the amateur radio community. But digital voice nets really are sort of floating around in there with the rest of them. Now, I came across this presentation on the internet. It was by K9EQ, and the title of it was Why Digital? And I think you could see that it's really simple and powerful, and it allows users to easily access a connected amateur radio world in the sense of global. Now, in case you might say, well, okay, what are these topics? What are some of the topics that are covered? Well, these are just a few of the notable ones that I picked out as examples. Okay, these are all D-star nets. And that's part of the problem. There's this, okay, we've got D-star nets, we've got Yaesu System Fusion nets, we've got DMR nets, we've got Echolink nets, et cetera. Again, they're out there. In fact, on on Saturday evenings at 9 o'clock on Do Drop In, there is a fantastic science net. And I'm really sad for the guy that runs it because it's relatively unknown. I don't ever see any listings for it, you know, so just word of mouth, he's got maybe 40 or so people tuning in, and who knows how many else listening on repeaters. Now, I think there are a lot of barriers right now, and this is where the M17 advocates are going to be really happy. I think that, you know, if we had some kind of a standard, and believe me, I'm not into standardization and ISO and, you know, everybody's got to do the same thing. That's not my mean. But the ability to tune in to anything. Now, I can sort of do that with my Thumb DV and the Blue DV software. So I can kind of do that right now. But, you know, in the beginning, think about it now. Everybody here is familiar with most of what I'm talking about. But what if you were starting out? What if you had just gotten a technician license and all you knew was the VHF repeater in town, and, you know, you sort of vaguely familiar with the fact that, yeah, I think they have a net. The club has a net at this time. So after they decide which mode, then they got to pick some hardware. How do we program that hardware? If your goal is to find digital nets, where are they? Which ones should I listen to or participate in? How do I find them? Who can help me? And honestly, I get a little bit of help from this guy. I got one person who is a DMR expert, and I get good advice from him, but, you know, ask him a D-Star or C4FM question, and it's a blank. So finding and joining digital voice nets is a complex undertaking. Most people start out, they just get their Baofeng, okay? And so, you know, that's fine, but then if they wanted to use that for digital nets, they either have to learn how to use a local digital repeater, and we're blessed in Aiken, South Carolina, where I live, to have a D-Star and a DMR repeater. So those are good. But there's a lot of choices. If you just started out with the Baofeng, then you got to sort of get a hotspot, or like I found out after I bought my hotspot and was struggling with Pi-Star for a long, long time, I could get a little stick and run the Blue DV, which is a relatively simple program to use. Programming software. Well, okay, I don't want to sit there all day and punch in a bunch of numbers, so I'll get some software to do it. All right, well, if I have the software, where do I go to get the information to program into the radio? Well, you know, it looks pretty simple on that menu there. That's a THD74 that I have, and, you know, you look at that menu and say, boy, well, just pick a few settings and you're in there, you know. Well, it doesn't work that way. Okay, what really happens is, you know, you open up their MCP software and all of a sudden you're confronted with all of these different choices. And here's the thing with digital, if you get one thing wrong, it's not going to work. It's not like it's going to work sort of, it doesn't work. And it could be very, very frustrating if you're doing it yourself. Okay? Now, this RT Systems, and I have 3 of the programs for different radios that I have. It is, the wonderful thing about it is you just go to that file, external data, and you pull in 35-mile radius for VHF, UHF repeaters. Okay? And that's what I have. Device programming and actions. You know, the Pi-Star, okay. You go to the main menu, and I do have to say this about Pi-Star. They have simplified the website, and it's really very nice now. They have everything broken out into little steps on there. But, you know, who knows that you have to go through almost all of those steps? Now, I use a stick, but you know, there's a lot of other products out there, and maybe somebody else has something better. Which one do I get? Chances are you're going to buy the one that your Elmer knows how to use, but is that the right one? Open spots, you know, those are, I don't even know if you can get them. I mean, like Raspberry Pis, very difficult to get these days. So, what do we have? Well, Brandmeister, TGIF, reflectors, talk groups, very confusing. So what I'm trying to illustrate here is there are barriers. These are very real barriers for somebody who is new to this whole field. And it took me, I'm still learning, you know. But wait, there's more. So if you go to the blue DV, it's, you know, there's only so many fields, it's one screen, and I think it's a lot simpler. Okay, barriers to using DV nets. And I'm going to try to leave some time for questions and answers. DV net listings, and I'm sure, okay, let me ask a question. Do you ever participate in DV nets, John?
On occasion.
Which mode?
D-Star.
Okay, and where do you find the nets that you're interested in?
I've been doing it for 15 years. So.
But no, I'm asking seriously, where do you go to find that information?
Yeah, the ones I participate in, I don't know if you want Mike, but the ones I participate in are mostly ones that I've participated in a long time, just a couple of nets.
Okay, all right, good. Anybody else regularly do DV nets? This gentleman over here?
I participate in 2 different D-Star nets. They're on Reflector 54 Charlie on Saturday night and on Tuesday night. And occasionally we have used a bridge to bring in other modes. We have the Carolina link, which bridges Wires X, C4 FM, YSF reflector, XLX, D-Star reflectors, and DMR talk groups, and have found that because of varying, through the bridge, varying latency, you need to do check-ins by different mode because they're a little different latencies. It keeps the net a little, running a little better.
Interesting. See, I'm learning something every day. This gentleman, did you want to make a comment?
I check in on Fusion Net on the down in Florida. The Lakeland Amateur Radio Club has a Fusion, like gather around the fires type net, if you will, at 18:30 hours for those that like military time every Thursday evening. And sometimes I'm mobile, sometimes I'm home, but they don't have a Wires X node on it. I'm hoping they'll add one, but it's just a chance to get on, say what you've been doing, and so forth.
My main question is really, how did you find out about it? Somebody told you? Or?
I was there when the net started, and it was word of mouth. And I was told, hey, we're going to start this Fusion net.
Good. But it's a limited data set that you're working with. And part of the problem of trying to collate this stuff, which I've actually done, well, I mean, I haven't done to the fullest, but I've actually worked on it. DVNet listings come in all sorts of forms. They come in different types of documents, different data record layouts, spreadsheet formats. Some of them, most of them you can just kind of copy, if they're in a form on an HTML web page, you can just copy it and paste it into a spreadsheet. But there are times when, for some reason, it will not paste. It just, each item is in its own separate box. Now, somebody who's really familiar with HTML will probably say, yeah, but if you did this, it would go easily. Now, a lot of times I'll just paste it in as CSV, you know, just a comma-separated value file or tab-delimited file, and then, you know, make a table in the word processing program. And I use LibreOffice. Okay, here's a traditional net listing. You know, and this guy, or gal, I'm not sure who, N1YZ, does a fairly good job. He color codes them. It's nicely laid out. But notice something here. See that time format sort of in the top third of that, the first two columns? It says 2400, and then right below it, it says 1000, or 100. That is another big problem in this. People will give different time zones. They'll put it in UTC, which is fine, but you know, maybe I'm just a little dumb, but I don't know how to calculate minus 2 hours or 3 hours for Eastern time zone or 5 hours for UTC or whatever. That's difficult. And I haven't been able to do it. There's all kinds of listings. Here's a really pretty listing with, I think the tourism department probably put this together. But these are different nets, the 9 o'clock net, the Alaska morning net, which is pretty pervasive. A lot of people all over the world check into that. Now, this is the same information, just on a different page. Oh, I don't know if I'm set up for internet down here. I forgot to do that, so I will. Yeah, there we go. Okay, here we go. Now that's parsable. I can parse that because there's some discipline in there. Notice that it's Mondays at, Tuesdays at. I can search and replace the space, AT space, and replace it with a tab. And by doing that, it takes a while, but it creates a tab delimited file, which I can then put into a table and, you know, sort of work with it. But then it goes into a spreadsheet from there. All right, here's a very nice listing. This is, you know, D-Stars nets. My guess is that this is probably 50% of what's really out there, maybe even less. But they do have a good, you know, net list out there. And you can even download it. So that's cool. Again, another net listing. Yeah, that's one of the people who I know. I was sort of asking more like for information gathering, not for my own interest, but I asked someone, well, how do you find nets? And they said, oh, it's easy. Just go on NetLogger, and you know, you can find the active nets right now, which are mostly HF, some VHF, and a few digital at the moment. In other words, when you log in and take a look at the current nets. But then there's a feature where you can go into the NetLogger control and look at past nets. And that has 3,500 plus listings, except that there's a lot of duplicates in it because some of them are daily nets or twice a week or whatever. And so you can see, what I'm trying to show you here is that the variety of formats of these existing lists is very, you know, it's just a mishmash of different things. Here's another one. In fact, this is the one I mentioned a little while ago, TGIF TG358 CSRA, which now has morphed into CSRA multimode net. Okay, but he has a net listing, which is, you know, for an individual, it's a pretty good list, you know, but it's still a variety. Then you get into these situations with the multi-modes where, you know, you have these huge repeater networks that have every single connection under the sun, including, not here, but I've seen also M17. And I guess, is anybody here sort of involved with M17? Okay.
Website, and they now have an M17 interface.
Yeah, I see it from time to time. And now, is it actually in use? I mean, not that particular one, but it's being used, right?
Well, the East Coast Reflector basically supports all modes, and it's just a question of where is the, you know, bridging interface for them, but I mean, if you look at that website, it's amazing these days.
Well, the goal for them probably was let's get every single mode that's used and put it on here, which I think is the same thing with the is it Little Mountain? I don't know. But anyway, it's LMARC for me. And this is me tuned into the TG358 talk group, I believe. Nope, C4FM. Okay, PAPA system. Now, you wouldn't know it. In fact, it's kind of difficult to figure out what they have. Is anybody familiar with the PAPA system? What? Not that well. I know it exists. Is it Josh? Jason. I'm sorry, Jason. Jason? What's on that system? I mean, you've got check-in nets, I would imagine, but also you have topical nets. Is that correct? Oh, okay. Well, as far as I can tell, there's like almost a dozen different topical nets where you have a D-star-oriented net where they talk about D-star issues or problems. If you have a problem, bring it to the net. Okay, they have an antenna net, which is shown here. Here's a local group. Now, I'm going to kind of segue here into how do you manage all this stuff so that you can get a comprehensive, easy-to-use database of all these nets. That's my key point. There is no single place that you can go for a comprehensive, up-to-date list. Now, obviously, just like internet, you're always going to have broken links or out-of-date something or other because they stopped it 2 weeks ago. But pretty much up-to-date, comprehensive in one place. Well, Augusta HamNet is nice because it utilizes this feature where you can actually put your calendar, put this calendar into your Google Calendar with just a couple of clicks. And I'll show you that in just a minute. Let's see here, where is it? You can download a copy of the spreadsheet. All right, here it is. Now, they've laid it out as an ICS form because the guy that does this used to be the emergency management director for Columbia County, Georgia. But, he's got all of the repeaters in here, but he also has he has a calendar in there, as you can see through here. And with this, I think the button is actually out of the slide, but you click on one link, and if you're on the internet, and obviously you would be, it can go right into your Google Calendar as a separate listing. Now that's if the person who made the calendar enables that. So if they don't know about it, then the feature's not there. But here's the little button right down here, as you can see. And I'm sure there are some percentage of you, probably a majority, that use Google Calendar, except that you'll realize that after about 3 or 4 nets, you don't really see anything. It just says 3+ or 4+, and you don't actually see the listing. So you have to go to the daily agenda to see 1 day's worth of nets, and then it's laid out on an hourly basis. Here's a site that presents a spreadsheet to download. Why is that? Okay. Again, CSV file for download, just like the D-Star. Now, in terms of models to follow, there is sort of a model, and that is the ICS type file. How many of you are familiar with ICS files? John? You know what an ICS file is.
My name.
Okay.
I don't use it. I'm not in
Oh, okay. Well, ICS, maybe not, and you know, maybe it's kind of unknown, but an ICS file is, you can use it for those V cards that you can put right into, you know, if somebody has a V card, you can click on a link and it'll go into your address book. Well, you can use, actually that's another component of this, but in any case, you know, it's a file that is meant to be Internet calendar standard. It's used in Internet calendars. Now, this is a set of links, and obviously I'm not going to go to every one of these, but at each one of those sites, and again, this is a partial list, at each one of those sites, you're going to see a different kind of list. You know, it's either a different kind of mode, etc. And actually, you can, like Netscraper. Okay, if you go on Netscraper, these are the active nets right now. But this one is not really used that often. I mean, it's, you know, but you can look at the past nets, and maybe this is the one that I was thinking of when I said 3,500. Anyway. Okay, so this slide, and these slides will be available somewhere, I'm sure. Is there a plan for putting this?
They will be posted on the TAPR site after DCC is over.
Okay.
That's on time.
All right. Now, here's one that covers a lot, you know, several different modes. But when you really get into it, you find that some of those modes are only like 8 or 10 nets long. So really, trust me, there is no, oh no, this one is a Facebook group where, you know, if somebody wants to put a net up on the discussion to promote their net, it goes in there. But then, you know, 2 days later, it's way down the list because somebody posted other information. So you can go to these different lists, find different formats, Echolink nets, DMR, Brandmeister, everybody knows about Hoseline, Quad nets, the East Coast repeater, or East Coast reflector that John was talking about, et cetera. So each one of these is a means of finding nets. Now this is ARRL's page, but honestly, it's kind of difficult to work with. Do we have anybody from, any officials from ARRL in the audience? Other than like a section manager or something? Okay. Well, I hardly ever use it, and I'll tell you why. Let's see here. First of all, I always have to look around. I mean, that's not pretty obvious. You really have to look for that. Okay, then you're up against all these selectors, and for most nets, you have to select a state, or you have to set a type of net for almost all of the searches. So if you're looking for a digital net, it's just not there. Okay, this is a quote from Eric Baxen, KC9ASC. He is the founder of that CSRA multimode net that I do every Saturday at 8 o'clock. I support his net. I log on, as you know, it's like 10 minutes, okay. There are lots of different calendars out there, so we're familiar, as amateur radio, I won't say hobbyists, as members of the amateur radio service, we're familiar with all these different calendars. Some of you are into contests, you know, events, Hamfest, Lookup, et cetera. Lots of different kinds of existing calendars. Now, a potential solution, and I wish I had numbered these slides. Just want to quick see which one I'm on. 38 of 42. Well, looks good. Which one is that? Oh, yeah, thank you. Ah, not good. Yeah, I just clicked the wrong one. So I hope these slides are a little entertaining. I try to, I've spent a lot of time doing presentations, and okay, a potential solution. And this time I'll be more careful. Start from, I'm using a trackball, so it's a little, okay, the first thing that came to mind for me was, gee, wouldn't it be nice if there was this cable TV-like calendar? I'm sure almost everybody's familiar with, not so much, well, I guess they still have them, but on your local cable system, you'll see one of these landscape mode calendars with all these different colored blocks, horizontal rectangles with the name of the program, the channel that it's on, and the time. But that's probably not really the best way to do it. I don't know. I don't know what the best way to do it is. So what's needed, if there was a project to put this all together to centralize and really promote digital voice nets, what would be needed? Well, the stakeholders. I would look at the stakeholders first. Who are the people with interests in this? And I think, aside from me, there needs to be a large organization partner, not necessarily a funder, but a partner, a sponsor, somebody to promote it, get behind it, have their stamp of approval on it. Some of these amateur radio calendars are very good and they're comprehensive. Now the net, so in other words, they might want to expand their listings. First, I don't know how many of you take advantage of it, but on Repeater Book, if you click on the call sign that comes up in the list, you will be able to go to a page that's devoted to that particular repeater. Well, a lot of times if they have nets, especially if they have multiple nets, the nets that are on that repeater or carried by that repeater are listed on that page. So there are a lot of different people and organizations that could be potential partners or interested parties or stakeholders. Now, how to assess this? I don't have a huge crowd here today, so I'm not hearing a lot of cheers, go Dave, let's do it, So how do you assess interest? Well, it's like anything. It kind of percolates over time, but if you build it, will they come? I think to put something substantial together, it is a multidisciplinary event. You need all kinds of people, not the least of which would be PR and promotion folks, to really promote it so that people know that it's out there. Now, this would actually benefit the radio manufacturers because I think more people would buy the more expensive digital mode radios instead of these crappy little Baofangs that they buy. Pardon me. Okay. Now, that's it. So we have some time for questions.
One of the issues here is there's some terminology ambiguity, and net in particular is ambiguous from the perspective it's being used to reflect, meetings, yet it also is used to reflect interconnected systems.
Oh,
and
yes. Nets and networks.
Yeah. And so that, introduces some ambiguity that if you're not, can be confusing. So, like the East Coast Reflector is really a system, but then they have a number of scheduled meetings on it, on a regular basis, which could be referred to as nets, because that's, common within the amateur terminology space, but, it can get confusing.
Yeah, and even beyond, and when you look at East Coast Reflector, there's QuadNet, which you know, I'm not really sure what that is. It's not spelled out. As a journalist, I was trained the first reference of something, you always spell it out. Put it in parentheses if you're going to use an abbreviation.
Yeah, so I wanted to follow up to one of your earlier questions. One of the problems we have is we do use acronyms. ICS is the Incident Command System, as well as the Internet Calendar System, and I am familiar with the second one.
I'm sure a lot of, you know, everybody.
So I understand your concern, and the problem with any of these, including repeater listings and stuff like that, is there is no master. Everything is self-reported kind of thing. And if we had a system out there that, much like the RSS system for websites, where there was a standard for recording how a network is named, what time it's held, what frequencies, a common timestamp, UTC, and then web pages could be built that would look at that timestamp and put it in the browser's local time.
Yes.
I've done that on a number of pages. And an export of an ICS file makes a lot of sense. So just some support to what you're saying there. But any of these projects require massive cooperation that is not a hallmark of amateur radio. And a standard that is built that covers all the various categories.
When I was sort of starting out in marketing, I made the transition from PR to marketing. I was very heavily involved in the aviation industry, mainly general aviation, business jets, private pilot stuff. And I was absolutely amazed when I found out that there was a list. I was marketing aviation department of flight management systems for departments to maintain their aviation or their maintenance records, all that stuff. And I had a client that had a software very early on. I mean, he was really the first that had a comprehensive system. And I was amazed when I suddenly realized that every single one, or no, just about every single one of his potential customers was a member of the National Business Aircraft Association. Now, those were the days when they didn't even have electronic lists, so I had to go through some rigmarole to get that, and then we printed them on labels so that we sent out mailings through the labels. But what I'm getting at here is you can target a lot of different small segments that have a specific interest, like the frequency coordinating people. They're into repeaters. And so raising their awareness of it, I think, would be just one public. And then people who, actually, that raises an issue that I've thought about is, do people that have nets want more people? And in my paper, I sort of treated that with, well, yes and no. You know, a few people would not want to have a local net listed. But we're delighted when somebody, I'm the net control for Monday night on the Amateur Radio Club of Augusta, nightly 2-meter net. And, you know, we're pleased as punch when somebody calls in via Echolink from Alaska or God knows where. You know, they happen to stumble across it and they just decided to say hello. You know, and I try like crazy to draw people out instead of having just one of these, you know, roll call, okay, now, you know, short time stations, Alpha through Lima, you know. Anyway, any other?
Well, that's about all the time we have. Thank you very much.
Sure.
Well, now we move into lunchtime. We break for lunch now, and please be back at 1 o'clock and we'll start the lightning talks. If you have a lightning talk, write it down on a piece of paper and hand it to me, and we'll put you into the queue. So enjoy lunch, and we'll see you back here at 1 o'clock.
So unfortunately, the two M17 guys and the Papa guys are out of the room. But we have plenty of them here.
Yeah. Well, I hope that, that takes off.
Okay. Well, it's whoever I want to choose.
Yeah, if we can put the belt back on, we can be more.
Everybody's and let's see, Jason? Okay, and good? And then you're good? Ready to go? Okay, thank you, everyone. Welcome back. It is, well, it'll soon be, yep, there we go, 1 o'clock. We're going to enter into the next 40 some odd minutes for lightning talks. I've got a whole fistful of cards here, so we have quite a few interesting talks. And a couple of our speakers will probably be wandering in pretty soon. The very first speaker I'm going to queue up here is this gentleman here about the Internet Archive, which has also been funded by ARDC. So here's a 5-minute presentation fire talk.
Hi, I'm Kay Savitz, K6KJN. I work for the Internet Archive. I'm in charge of building the new digital library of amateur radio and communications, and I need your help. First things first, if you don't know of the Internet Archive, it's a nonprofit online library that's been around for 26 years. It's best known for the Wayback Machine, which is a tool that allows you to go back in time to see websites, how websites used to look, or to see websites that no longer exist. Internet Archive maintains a freely accessible online digital library holding more than 40 petabytes of data, 700 billion web captures, 2.5 million films and videos, another few million audio recordings, 8 million textbooks, and including 3 million digital books, more than 250,000 pieces of software, and 2 million hours of recorded television. That's all at archive.org, and you should check it out if you've never seen it before. Now, Internet Archive is building a massive library of ham radio. Thanks to a grant from the Amateur Radio Digital Communications Foundation, we're building the Digital Library of Amateur Radio and Communications, an online, open access resource to preserve the past, present, and future of amateur radio and communications. The library will provide an open access educational resource that will be free for everybody to use. We're aiming to create an unparalleled collection of resources, ham radio books, magazines, newsletters, podcasts, videos, from material published today back to the beginning of ham radio 100 years ago. Internet Archive got this big grant, and now they've got me to do the work, and now I need your help to make it happen. I mainly need two things. One, your donations of ham radio related material that you think should be included in the library. Got stacks of ham radio books and magazines and newsletters on your sagging bookshelves? We want them. Internet Archive has the capability to scan and digitize vast amounts of material. I won't turn away any collection for being too big. We'll add metadata and full text search to all of the printed material. I especially want unusual stuff. I think runs of QST and 73 won't be too hard for us to fill in, but I want the obscure ham radio club newsletters and technical publications and manuals and catalogs and old radio lessons on videotape and that sort of thing. Internet Archive will respect the copyright on donated physical material through controlled digital lending. Say you donate a book to the Archive's library, we will scan it without cutting off the binding or harming it in any way, and then permanently store it. The digitized version of that book will be available to one person at a time via controlled digital lending. It's an electronic version of a traditional role of a library that lends out material to one person at a time for a limited time. I said I mainly needed two things. Here's number two. If you're a content creator, I want your permission to share the ham radio related content that you've created in the library. Radio related podcasts, your YouTube video channel, your ham radio site, or your blog. Those are a few of the amazing things content creators have already given permission for. Personal digital archives such as photographs, scans of your logbook, documentation of your de-expedition on digital video, your QSL card collection, great. And you don't have to give those physical items to the Internet Archive. If it's already digital, you can just send a link and your permission my way and we'll get it included. If it's photos or a journal or other printed material, one-of-a-kind stuff that needs to be scanned, we can scan it and return it to you. You already have a web server for your blog or website or whatever? Sure. Putting it in this library will increase its visibility and findability and provide a permanent backup for your content that should be available many, many years from now, even if your website or blog goes away. So that's my pitch. The Digital Library of Amateur Radio and Communications is going to be an amazing resource for current hams, future hams, students, researchers, and radio nerds of all stripes. This enormous free digital library will put a lot of the past and present of ham radio under one umbrella. If you'd like more information or are ready to be part of this project or just want to empty your shack of the piles of old radio books and tube catalogs, email me at k@archive.org. 73, and thanks for watching.
So good suggestion there, John. Okay, so that's a fascinating thing. We should preserve all our information. All right, so that takes care of that. So Jonathan, let's do you next.
All right, now make sure you tell me if I'm over or under modulated. I am not a quiet person. So, good afternoon. My name is Jonathan Brandenburg, Kilo Foxtrot 5, India Delta Yankee. By day, I work for an engineering company out of Houston called Medics, and we specialize in aerospace flight software, robotics, simulation, immersive environments, that sort of thing. And earlier this year, I was charged with developing a Helmholtz cage, which is what I'm here to talk about briefly today. So what is a Helmholtz cage? A Helmholtz cage is a device consisting of concentric electromagnets. And the purpose of this is to somehow create a magnetic field. In my particular case, I wanted to both cancel out the ambient field that's around us all the time and then reproduce a desired magnetic field of a satellite in low Earth orbit. Why? Well, you can probably think of some reasons. One of the things that my organization, my company is doing is we're developing attitude control algorithms, initially, for example, to detumble a satellite coming out of a deployer. And you can often do that using a magnetometer to measure the Earth's magnetic field and then torque rods to counter against that Earth's magnetic field and slow your rotation. So at the very beginning of this year, I was charged with doing this, and honestly, I kind of had no clue. I was a bit overwhelmed. So what do? You give it to your interns and say, go at it. And I'm not sure quite how this works because it's happened a couple of times in my experience. I'm overwhelmed by something, I give it to my interns, and somehow it magically appears. In this particular case, Jonathan Lefauq and Adam Moore, with an Elmer by the name of Mike Zirkus, very quickly assembled an 18-inch scale model of a Helmholtz cage, including power control circuitry and a simulation that would drive that circuitry to simulate the field of a satellite in orbit. And frankly, when they built this, it's a little, the coils are not like perfectly uniform, but I'm pretty impressed with this, right? I kind of want this at my home, but my wife will probably push back a little on that. So what we did from there, though, is we then had to build a full-size Helmholtz cage. What does full-size mean? Well, that's kind of arbitrary. In our case, we wanted to be able to ultimately simulate a volume that was capable of holding a 3U CubeSat. So we wanted something in the volume of 24 inches cubed. And I'm taking somebody else's word for this, but it seems that it takes space or volume for the magnetic field to stabilize over time. So by creating a 7-foot diameter coil, we were able to get a standard, stable, uniform magnetic field in the center of that volume that was capable of about, again, 2 foot cubed. And so that's where we are at. Now that looks very impressive, honestly, sitting in our workshop down in Houston. My boss seemed to like it because he put a sign in front of it that said, "Please enter target date and time before entering time machine." I really did like that, and I personally, and this is a little more juvenile, I want to put Christmas lights on it because anything this impressive should have flashing lights. That's kind of the way I'm looking at it. Yeah, it may impact the magnetic field a little bit. I'm heading down to Houston next week after I get back to reinforce those coils. There's an aesthetic issue with it where the coils are actually sagging a little bit under their own weight. So I want to make that look a little better. And then I'm going to be prepared to begin initial testing of the magnetometer sensor and the actuator torque rods that we're wanting to exercise with our attitude control algorithms. And to kind of bring it back to this audience, it's not a coincidence that the magnetometer sensor I'm using is the exact same sensor being used in the Personal Space Weather Station. So with that, I quickly end, and I think I have time for questions, if any. Or not. One last picture. Can you reach?
Yeah, thanks. Well, yesterday we were talking about calibration, the magnetometer, but how do you calibrate your Helmholtz cage?
Yeah, the question is, how do I calibrate the Helmholtz cage? How do I know that it's generating the desired field? There's really two answers to that. Number one, what should the field be, right, for a given, and there are databases that provide that, so that's not too hard. But the second thing is that if you look really closely, and I don't know that I have a cursor here. Will the cursor light? Probably not. I do. And it is showing off, and now it's showing on. There we go. That little device right there is a laboratory grade magnetometer that we are currently putting in the center of the cage. Now, I made a mistake and I bought a 1-axis magnetometer, so we actually have to turn it manually for the 3 axes, but it's my desire to buy a 3-axis magnetometer. And we also have plans actually to create an automated gantry to move the magnetometer through the volume in a controlled manner so that we can map the field. Long answer to a short question, so I hope I got there eventually.
And there's some kind of NIST connection?
There's some kind of NIST connection. When you say NIST, the answer is no, because if I'm understanding right, we're using the geographical survey database that tells us what it was or what it was like a year ago or something like that, and that's close enough for our needs. How am I doing on time?
You're doing good. Any other questions? Okay, just a moment.
Once again, please forgive me for asking a very basic question, but what will you be able to do? I mean, I know it's putting a CubeSat in there and turning it or electrically looking at it, but what does that do?
So I'm going to take a simple question and maybe make it more complex than you wanted. But there is an algorithm that will use the measurements of a magnetic field from a magnetometer, again, like the one used in the Personal Space Weather Station, called the B-dot algorithm that basically then feeds into magnetic electromagnets in your satellite that then create artificial fields that react against the Earth's magnetic field, kind of like putting two magnets together the wrong ways. It pushes back. We can do the same thing with a satellite and counter torque the rotation of the satellite. a non-rotational gyroscope in a manner of speaking, I suppose. But we are actually ultimately putting in reaction wheels into this same simulation. Now that doesn't work with the magnetic field of a Helmholtz cage, but we're actually creating rotational test frames using low friction air bearings and motor assisted feedback loops to test the reaction wheels as well. I'm probably getting real close on time
That's
now.
about
All right,
all the
thank you
time.
all very much. I
Thank
appreciate
you.
it.
Need a little wood table in there.
I have a order to build one.
No screws, no bolts.
Phil, let's go ahead and take you next. Let's see here.
Okay, this is a quickie talking about a proof of concept of something I'm showing the other room. So if you're interested in a demo, come on over. This is an application of the multi-channel receiver SDR that I talked about last year. So go back to last year's proceedings for the details. And this is just one application that I came up with recently. I thought was kind of interesting. So last year I talked more in detail about this radio, how it uses fast convolution, IP multicasting. It all runs on general purpose CPUs. I've since made it, really sped it up and made it a lot more efficient. I'm now able to use a single Raspberry Pi 4 to demodulate every FM channel on a single band, like 2 meters or 70 centimeters at once, and do that easily on about half or 2/3 of a Raspberry Pi 4. I've been recording all of the 2 meter, 125 centimeter to 222 to 225 and 70 centimeter FM channels in San Diego since the beginning of last year. I have no idea what to do with all this data, but hey, maybe I should send it to the Internet Archive. About 2 terabytes right now. I'm actually getting calls from repeater owners saying, we got this jammer on our repeater. Can you give me some recordings? So maybe it actually has some use. The code is all up on GitHub, K9Q Radio. I'm trying to keep that pretty up to date. So anyway, what I want to talk about is this idea I've had for an application of K9Q Radio. Those of you who know about the FM repeaters have been flying on a number of low Earth orbit satellites, AMSAT, CubeSats, and the ISS also has a repeater of this type. Know that this has some drawbacks. There's only one FM input and feeding one output, and everybody knows about the FM capture ratio phenomenon that, for anybody to win, that person has to be at least 10 dB stronger than the sum of everybody else also trying to get into the repeater at the same time. And often there is no such person, so nobody gets through. So it just doesn't work very well. But suppose you had a repeater with multiple inputs, all summed into a common output. And those inputs are all equivalent. You can pick any one of them at random and they'll all come into the output. And if everybody actually spreads out and picks one channel at random, it seems to me that this actually has a chance of working reasonably well. This is not a new idea. We had the same idea back in the late 80s, over 30 years ago. We used it in PACSAT. There we had 4 uplinks, all of them which were equivalent. The receivers were, in those days, hardware, so we really couldn't have more than 4 uplinks. But, we did it on several PACSATs, and we were launched in 1990, and the idea worked reasonably well. So why not just apply it to voice as well? So that's the idea. I mean, it's a very simple one. Let's see, how many slides did I do anyway? I guess that's it. Yeah, all right. So if you want to see this working in the other room, I'm happy to demonstrate it. It's just one application of many that I think you could make of this multi-channel receiver. Eventually, I'd like to have the downlink be digital, but we want to fly this on a balloon, and to do that, we're going to have the downlink be analog the first time. But eventually, I want to have the downlink be digital, so you can keep the channels separate. In the analog mode, they'll all be summed together. My big worry there is there may be interference or noise on one channel that, drowns out the others. That is a concern that I have. John, do you have a?
Just a moment.
Have what?
When you say that the outputs are all summed together,
Yeah.
what do you mean? Is it just into an audio stream? of
Analog
everything?
summed, yeah. There's just analog summed. So in fact, I had to make very few changes to make this work. There's a monitor program I talked about last year that receives a bunch of these streams, each one coming out of a logically independent voice over IP stream, and sums them into a speaker. Basically, all I had to do was to add a PTT algorithm to key the transmitter when any of them were active and a CWID. That's basically all I had to do. Now, I'm also thinking, well, what about a courtesy beep? Well, you don't really need a courtesy beep if several can transmit at once, unless you want to tell people which channels are being used, so they can pick one that isn't. So I'm thinking about this stuff. All the usual assumptions about how you design a repeater kind of go out the window when you have when you have multiple inputs like this. In fact, a lot of the issues about receivers go away when you suddenly can handle hundreds of channels at once.
So we'll take 2 questions and then we'll wrap it up.
Couldn't you use just regular analog receiver voting with using noise, the way a lot of analog repeater systems that have multiple receiver sites do?
You mean like voting systems?
Yeah, voting system.
Well, a voting system is designed for just one user who may be received at more than one site. Here I'm having several independent transmitters all transmitting on their own channels. They're transmitting different signals. And so I like to just have them all just be combined and summed coming down. Now, I mentioned earlier, my concern about interference. I already have a tone squelch on each channel. I think most FM repeaters in orbit have tone squelches, I assume. I haven't actually really used them myself. And I'll probably also tighten up the squelches. So, getting a link solid enough, I don't think is going to be a problem. Not into a LEO, where the problem is people are running too much power and not enough.
I know that with with satellites, if you're on sideband, they use a translator, which essentially the frequency coming up translates to a frequency going down, and you can actually have multiple conversations there.
You can.
So I wanted you to describe what's happening on the transmit or downlink side.
Okay. Frequency translators are an hallowed idea in amateur satellites. The very first transponders were made that way. The problem is that they create the problem of power imbalance. Everybody going up has to be received at the same power level for this to work. This is a 50-year-old problem that AMSAT has never been able to solve. Getting hams to actually control their uplink power so they come down with it. It's just not, after 50 years they can't solve this problem. I don't think they ever will. The advantage of doing it this way is that it doesn't matter how much power they're all running, because each one will saturate their own receiver and not affect the other ones. Unless, of course, they're transmitting so much power they just overload the front end and wipe it out. So
what about the same idea for the transmitter? I mean, think about it. You could have one receiver like this.
Right.
With multiple inputs, one transmitter with multiple outputs.
Yes.
And that's the
what I eventually
entire
want to do.
area's repeater for 20, 30, 40 stations.
That's what I eventually want to do. What I want is for the downlink to actually be a single multiplex digital stream with each of the uplink streams as a separate logical stream in the downlink. In fact, that's what I'll be demonstrating in the other room, because the transmitter is kind of virtualized. I was going to I did bring a hardware 2-meter transmitter, but I wasn't able to get it working in time. So ideally what I want to have is a single high-speed downlink with each stream logically multiplexed on it, so you actually can, at the receiving station, mute the channels you don't want and actually form a QSO, round table with a subset of the uplink channels that are members of your round table. Yes, you can easily do that. Not with the analog FM downlink, but with digital downlink, sure.
Okay, we got one last question in the back. You still want to ask your question? No? Okay. All right, we're done. Okay. Thank you very much, Phil.
Come in the other room and I'll show you. Thanks.
Yeah. As Phil mentioned, that he's going to be demonstrating this in the demo room, so that's a great opportunity there. Okay. Christina. Let's see. Keep waiting. There we go. Okay, I'll let you drive.
Hi, folks. So this was something that I was asked to talk about. How many people here are familiar with Jupyter Notebook? Okay. So what I'm going to show you here is a handy-dandy little Jupyter Notebook for looking at results of regular data collection from the Lowell Digisond network of vertical ionosons, which let you see, various ionospheric parameters at different times. You can find it here at github.com/kcollins/didbasefetch. And it's a good way to get started with trying these out. I'll see if I can get this to open properly. Perhaps. I may not be able to, but if I cannot, you should go to that page and click Launch Binder. And it will, here is a preview of what it has, if it does not cooperate with me here. So what these let you do, and this one happens to be running a Python 3 kernel, I think of Jupyter Notebook as being kind of a chicken pot pie software solution, because it is wrong to meld dinner and dessert, but it's so delicious. And it works pretty well for that. What it lets you do is it lets you put exposition in the form of markdown text or LaTeX in the same file as little cells in which you're executing, for example, Python code. And for this reason, it is very popular, as you can imagine, for scientific analysis, where you're putting in a one data set from one set of instruments and you'd like to compare it to another set of instruments. It's quite good for that. So a lot of these scripts that we have for looking at ham-sci things are in the form of Jupyter Notebooks. And Binder, the system that this would be running on if it were working, but alas, it is a demo and therefore it is not, lets you run it on a server that someone else is running, and so we don't need to worry about installing any of the dependencies to your local machine. It's probably fine. I can try. It might just be that the network doesn't want to. If anybody, I had it running on a local machine. Let's see. Yeah. I'm going to take a quick look and see if I can open the cached version on here. Oh, good. Yeah, you have a plot. Cheers. Yeah, I'll just walk through it briefly. I like to recommend this to people partly because you might want to see what ionosons are doing on a given day if you're trying to figure out what's going on, and also because it has several of the basic things that you would like to do in a Jupyter Notebook. This little number on the left is what order the cells were executed in. You do that by putting your cursor in it and going Control-Enter. So it's, if you're somebody who's very used to the MATLAB IDE and you're trying to get more comfortable with Python, it's a really good intermediate tool for that. So, this happens to be pulling from the Lowell Ionoson database, and for that you can construct these URLs. I apologize, this is going to be a bit of an eye chart. If this were loading, you would see a CSV file of, I'm surprised that one's not. You would just have the date and time and the information. Maybe it did. Okay, so this is the type of thing that it's crawling, which, you know, just a familiar, header data, and then the thing where you do the width, but not delimiters. Blanking on the name. That. Thank you, fixed width. Yeah, so it's just scanning one of those, and then it generates a pandas data frame, and then generates an interactive plot not shown in this version. But again, Should you wish to go to github.com/kcollins/didbase-fetch, you might perhaps be able to run it on your local machine. Cheers, thank you very much.
Exciting, exciting. Okay, we got that. And okay, Bob, I think we got you up next. So we have all right, this one's your where's your second one?
It's on a different file, so we'll just do this one.
Okay, do this one now. All right. So you've got come on. All right.
So I'm involved with a group that's working with global meteor cameras, and the idea is to buy some inexpensive little camera modules, and these are like $40 on eBay, and set them up and copy meteors. So here's an example of meteors that I captured from my house in North Texas. And this happens to be during the Perseids meteor shower, and there were like 50 meteors that night. But almost every night I catch a few meteors, like up to 7 or 8, I'd say, on an average. And this network is growing at a very fast rate. So if you're interested in this, if you do a search for Global Meteor Network, you can get all the instructions on how to do it. They're running with a Raspberry Pi. There's a software package you download and install. It will capture the data files from the camera, configures the camera. The camera is a Sony camera that's got very good night vision. It sorts through the data and decides what's a meteor and what's other stuff. And if you look at the files, well, if you look at the files, you'll see aircraft are usually blinking lights, and the meteors are long straight lights. The real goal of the group is to find fireballs, the ones that explode. And the idea is to have multiple cameras, and they're really efficient at being able to triangulate the meteor so you could figure out where it hits the ground and go maybe find some fragments. And this is a worldwide network that's growing at a pretty fast rate. The other interesting thing is the thing will backtrack to figure out what the progenitor or the location the meteor fragment or the dust came from, and show you your meteors. It breaks them down, the ones that you received on your camera. And then at the bottom down here is the meteor storms that are predicted to happen as the Earth is progressing around the sun. So you can get a feel for the possibility that you would see meteors. Now, from an amateur radio point of view, this could be interesting for meteor scatter. And so one of the things you could do with this kind of data is predict your ability to effectively utilize meteor scatter. And I hope to eventually be monitoring some of the microwave beacons and try to correlate meteor scatter data with the data that I get from this thing. It tells me the time. I can see the time for each of the meteors. You also see star tracks from the Earth rotating in here. So it would be possible to look for variable stars if you wanted to, if you were interested in astronomy. You could use this camera for that purpose as well. Okay, so let's go to the other.
So that finishes Bob's first talk. Any questions? Oh, we got lots of good. Bob, you're going to have to do some deal with some questions. Oh man, the room lit up here.
Okay.
Thank you. Do you guys have any overlap with NASA's citizen science projects?
Well, I don't know for sure the answer to that question, but I know that the guys, there's some guys involved in this that are real heavy into it, some of which are being funded by NASA to do tracking and meteor science. And there are some of the guys that are actually created the software. There's a good handful of them distributed around the world that are involved in this, very good at responding to questions and help if you need it. And also the British group is also very active. They got a lot of cameras in Britain. They got almost a full country covered.
Bob, can you repeat, if I Googled to get more information?
Global Meteor Network.
Global Meteor Network. Thank you.
I'll sneak through this way. Actually, you ended up with the wrong, I gave you the wrong one.
Okay.
Yeah, so that's why I blew off some.
Hey, Bob, you mentioned you're in Texas. How much light pollution is in your neighborhood? I live in suburbia where, you know, it's not so easy.
Well, I'm a little bit fortunate because I'm on a ranch north of Dallas, but there's a guy in Plano, Texas, that's also doing this, and he's having pretty good success. Yeah, there's a lot of, I'm not giving you a lot of information. Talk to me some more if you want to know more, but you can pick the angle of resolution that your camera has and control the amount of sky you have. And actually, they want you to utilize more sky using a low pixel rate, so the camera will download at a pretty fast rate. You don't end up generating a ton of data, although they archive the data every day. This is really for the science project, in my mind, it's a lesson in how to do this with the public involved, collect a bunch of data, have it go back to servers. These are video files. Have it go back to servers and manage it. The server automatically comes back and updates your software after you get logged in too on a daily basis. Your data gets uploaded every morning, and you can go to the worldwide database and look at your data and other people's to compare it if you want to.
My sky pollution is called clouds.
Yeah. Yeah, that's a problem.
So your algorithms to find the meteors, how good are they at filtering out satellite passes, especially like Starlink?
Yeah, they're pretty good. They're pretty effective. There's also some artificial intelligence packages that are being used against it too to help sort out what's really satellites and what's not. You can imagine with so much data, they really try to boil it down to just the meteors that they want to keep and throw out everything else. But with so much data coming at them, they can't do it by themselves, by hand. They got to have it automated.
Are you able to use optical filters to improve?
Actually, there's an optical filter in the camera, and the first thing you do is take that out.
Perfect.
But yes, you could potentially use filters. I'm thinking about modifying the camera, put a neutral density filter in there that's real dense and use it to monitor the sun during the day. You'd have to put an ASL a movement capability on your camera, but your location of your camera is very important, and the aiming, because you create a calibration file that they look back at all the stars you have in your image to know exactly where you're aimed. So they have that's all closed loop. It's really, really a cool thing. Okay, let me go ahead and go with the next
Okay,
one.
so we're going to segue now. Thank you for that talk. And then Bob is going to talk about loop antenna design and simulation. So do a reset of your mind right now.
Okay, so I have I'm in the Society of Amateur Radio Astronomy, and there's a project they have, which is a super SID, which you've been hearing all about, the SIDs and the SIDs events. And I've had that for a long time, and like a lot of us, kept it in the closet. Finally got it out, hooked it up, built a loop antenna, and connected it up. And it wasn't working very well, wasn't collecting very much data. So I started looking around thinking I need to get a better antenna set up. Found this fella, Richard Ganelli, had published this antenna back in 1963, and he was born in 39, something like that, just died maybe less than 10 years ago, and was a pretty productive fella, it seems like. But he had this full design talking about buying parts from Sears and Roebuck, putting this all together, and it was just cool, I thought. So, but what he did was he used some half-inch copper tubing, and this is an 8-foot diameter loop. At the top of it what he did was fed a rubber hose through it. I wouldn't do that. I'm thinking the wire is good enough today to stick with wire. I sweated on 1/2-inch copper fittings and screwed a 1/2-inch plastic coupler at the top because he suggests having isolation because you get static buildup on this copper tubing. And the tubing is there to help eliminate static so that you're just receiving the field, the EMF field, I guess, that you're getting in the air. And you can see that at the, I never did get this thing to work. It seems like it's turned on. I have one of these myself. How do you turn that?
You make it green.
Okay. Yeah, okay. So there's you see this is just a tunable inductor down here, and it's interesting, he calls out all these parts that are really no longer available, but you can find something similar. And then he's got a couple of capacitors here and a transformer essentially down here, which is like a ballon to get the impedance right. And his thing, he screws this all into a metal box. This goes into like a UHF or connector to come back on 50 ohm cable to your transmitter and receiver. He went with 16 gauge wire so he could put some power on this and not burn up his loop. And he talks about getting a ferrite rod, which I found you can order these on Amazon pretty cheap. You can find them. And you can get the 28 gauge wire on Amazon also, which is cool. And so I bought the wire and the ferrite, wound it, took an inductance meter and measured it. And then what I've been doing, he played around with his capacitors when he was operating. And I realized that for amateur radio, you would like to have a narrow bandwidth because you're going to operate a certain frequency. But for this science project, there's really a need to have a wide bandwidth. And I've actually asked, what do you want to listen to? And the answer was everything. Well, that's not practical. I think we got to narrow that down. But I decided to simulate this in SPICE. So I've got this whole thing played into a P-SPICE model and started looking at it. And let me just point out that this is what the Super SID looked like in 2013. And today it's not the same, it's different. But it's really just a single op amp. This one's being used for a reference. And on the one today that's a dual op amp, instead of using a reference, they have a buffer. They use the second op amp for a buffer. So in reality, they're only using one op amp, which is an FET input op amp, connected back to the antenna. Now the impedance of this input is a long ways different than this 50 ohm line that's over here. So my thought is, there's not much there. Just put that all out there at the loop. Get rid of the feed line so that you don't have to deal with all that. So in my P-SPICE simulation, when I start varying those capacitors, I found that this loop, this peak of this response really will walk around here, but the bandwidth stays pretty narrow. So for the science project, you really need a wider bandwidth. So I'm still working on how I might broaden that out some, but the other way to do it is to put some digital switching in there and just change capacitors on the fly. But then you'd be capturing bands of data and it would take a lot of time to integrate all that. So in that circuit, you could see there was a capacitor in the feedback, so there's an integration time. But the other thing is the phase angle is shifting and can change a lot. And part of the science project is they want to look at the phasing of signals as they come in. Now, they're really interested, I think, in a differential situation. So if it's not phased properly in the receiver, it's probably going to be okay. But you just need to be aware of that because you could have some other secondary problems. So that's where I'm at right now. I'm still working on the loop, but I'm going to end up with 2 of them, I believe. The downside is copper tubing is expensive. Okay. Okay, that's all I have.
Okay, wonderful. Thank you. Thank you very much. Now, I think that completes our lightning talks for today. Is there anybody I missed? I think we got everyone. Okay. Let's go ahead and we'll get set up for... So what do you guys think of the lightning talks? Yeah, it's kind of like a box of chocolates. Tom, I'm sorry, come on up. And it's this PDF?
Yeah.
Okay. Working on it. There we go. And you're all mic'd up. Okay, take it away.
Well, good afternoon. I hope everyone's still awake after lunch. Yeah, there you go. So this presentation is called Starlink, Arden, and Networking. The outline is talk a little bit about Arden, what it is, tunnels, client servers, Starlink, how it works, some issues with Starlink, and then some ways around it. Talk a little bit about Tailscale, which is a free VPN, very easy to set up, and using a cloud host to help solve some problems. So Arden is really outstanding software package for a range of commercially available wireless nodes. It repurposes a growing collection of 802.11 Wi-Fi equipment into the amateur band. It provides mesh networking, good link speeds, and the software in it also provides routing and advertises services from your local node out onto the radio network, so folks can look at your node on their list, click a service, and get a web page or a phone or something into that service. It's available for 2.4 gig and 5 gig amateur bands. There used to also be 3.3 gig links available, but that spectrum was withdrawn by the FCC action recently. One of the things that Arden has built in is support for internet tunnels. The recent versions of software are based on Lua. They reclaimed enough space in the ROM that those are no longer optional downloads. They are built into the base load. The tunnels are useful when, for example, the distance to a node is pretty far away, maybe too long for an RF path, or might require too many hops. The path might be obstructed. The tunnel client attempts to make a connection to a tunnel server on another node. And so the question is, what do you do if internet's not readily available at a particular node? So this is an Arden node at my house. This is a 2.4 gig link. It's pointed at a nearby mountain, and I've attempted to put about 10 degrees of up tilt onto the antenna because the mountaintop's about 10 degrees elevation. Starlink is a satellite internet service offered by SpaceX, which is an Elon Musk company, provides fairly low latency internet connectivity with a small portable flat phased array dish antenna. In some places, like where I live, it's the only reasonable internet alternative. I went from kilobits to megabits when I moved to Starlink, and interestingly, the pricing was about the same. So there are places where there are limited choices. It uses a constellation of thousands of low Earth orbit satellites, and in most cases, the satellite links you to a ground station. There are a few satellite-to-satellite laser links because there are some places where the satellite is not within range of a ground station, and so they link you satellite to satellite to a satellite that is within range of a ground station. The antenna is a phased array electrical beam steering antenna. There are a couple of motors on it, but those are used just during initial setup and alignment, and then the motors pretty much go dormant after that. And so the beam steering is all done electrically. They're running into capacity constraints now in certain areas, the San Francisco Bay Area in particular. There are more people wanting to use the service than there really is satellite bandwidth available. Starlink is working on version 2 satellites, which I think triple the capacity of the existing satellites. I think the V1 satellites are about 50 gigabits capacity, and the V2s are about 150 gigabit capacity. So this is the Starlight constellation. I grabbed this image on August 31st, and you can see all of the satellites which are in inclinations that up to about 56 degrees or something like that. So the satellites cover from about minus 56 to plus 56, leaving the polar regions open. There are some V1.5 satellites in polar orbit, and you can see a few of those. And so I believe that they do provide service to Antarctica in places now. And on the map, you can see where there's some cell indicators, and these indicate where coverage is available. You'll see a few streaks. These are where about 40 or 50 satellites were launched, and it takes the satellites a few months to spread out into the constellation. So after they're launched, there'll be a train of satellites that slowly over time space out into the desired constellation. So at home, this is my Starlink dish. This is a version 2 dish. It's 12 inches wide by 20¼ inches this way. And you put it up, turn it on, and in a couple of minutes, it'll orient itself correctly. It orients itself generally pointing north, so that it's got an elliptical beam pattern. It doesn't have very good coverage to the south and has very good coverage to the north. This is a good website, starlink.sx. You can bring it up, type in your satellite location, and it will give you an estimate of what you can see at any given instant in time. So in this case, I've typed in my satellite location in southern Oregon, and you can see the ellipse, which is the estimated antenna coverage for the antenna at that location. And then it will show you the satellites that it thinks you can see. In this case, there's about 9 satellites that should be visible at that instant in time. And it will draw a dotted line to all the satellites it thinks you can see in green, and then in brown to the Earth station that satellite would link you to if you're using it, and then a solid green line for the satellite that you would select at that instant in time. So you can see the path when this was taken was to this satellite, which then downlinks to a ground station in eastern Washington. And there's a ground station in southwest Oregon. They're kind of scattered all over the place. It's a great visualization. You can watch the beams snap back and forth, and it's, I think, a fairly good indicator of what's going on. The triangle here is the ground station in Seattle, and there's also a ground station in the Bay Area, and they're scattered all over. The blue links here are the satellite-to-satellite laser links, so that if you happen to be in a place, for example, out over the ocean, you might get an optical link back to a satellite that then links you down to a ground station. They're selling it to cruise ships, where they've mounted these on the cruise ships, and they can be out in the middle of the ocean and still get reasonable internet connectivity. So if you want, it's great fun to just look at that. You can stare at it for hours, depending on how easily bored you are. So the question was, can we run ARDN tunnels over Starlink satellites? And I got on the ARDN reflector, and there was all kinds of yes, no answers. Starlink's convenient because even where you don't have internet, you can get an internet connection, for example, on mountaintops or otherwise internet-less locations. What ARDN does to make a tunnel is it uses TCP port 5525 and establishes a TCP tunnel between what's called a client, ARDN node and a server ARDN node. And any ARDN node can be a client and or a server, depending on how you configure it. So it provides a way to temporarily perhaps establish ARDN connectivity while RF paths are being acquired, constructed, and put into service. Or if you have an ARDN node that's really out in the middle of nowhere and it's not likely you're going to build links, it still allows you to get on the air and provide connectivity to some other node. So I put this up, connected ARDN to my Starlink internet in the Rogue Valley. It's worked quite reliably. It's been very good service. I've had no issues. The ARDN node can easily be set up as a tunnel client, and it does not work as a tunnel server. And I'll go into why that is. So if I've set mine up as a client, and then I'm tunneled into someone who has an ARDN node that is not on Starlink, set up as a server, and that path works, and that connection works quite well. So the application is you might have an obstruction between two clusters of users, and the only practical way is to make an internet tunnel to connect those clusters of users. In our case, we have a couple of mountains. Unfortunately, there's two mountain ranges between these clusters, and so if you put a ARDN node on top of one mountain, it still can't see the other one, so you've got to put two up and then do a site-to-site link. And we've done that for a couple of those. The internet tunnel comes in handy when RF links break, go down, other things happen. So Starlink has some major issues. One of those issues is the standard Starlink does not provide a static or a dynamic IPv4 address. The address your router is given is not routable. And it uses what's called CGNAT, Carrier Grade Network Address Translation, sometimes called NAT 444. And it allows a single one IPv4 address to be shared simultaneously by up to 128 different customers. And that means that if somebody has your IP address, they don't necessarily have a route to you. And that can be a real problem. Each customer can have multiple computers. And in theory, you could have 30,000 computers on a single IPv4 address, which means you run out of ports real fast. One of the problems with carrier grade NAT is that the port entries time out, and sometimes fairly quickly. So you might get a dynamic port assignment, and within a couple of minutes, that port assignment can time out, and then people don't have a route back to you. So this, in general, prevents running a service. You can't put a web page up, you can't SSH into your node, and you can't provide an ARDN tunnel server because nobody knows how to get to you. Starlink is not currently supporting IPv6. It may in the future. They had IPv6 up experimentally, and then they turned it off right about the time that they shipped a bunch of terminals to the Ukraine. So there's a lot of rumors as to why they might have done that. So at home downstairs, this is the Starlink version 2 router. And out of the box, it provides Wi-Fi. I bought the Ethernet extender cable. What this node does is you plug it into AC power, and it provides power and internet connectivity up to your dish. It can take sometimes over 100 watts if it's trying to melt ice on the surface of the dish. Most of the time, for me, it draws about 40 watts. That phased array has got several hundred antennas in it and several hundred phased array devices, and all of that takes about 40 watts. I think the dish is actually running an embedded version of Linux inside the dish. You plug in this extender cord here, and it allows this thing to provide power up to the antenna, and then breaks open some connections and gives you an Ethernet connection to your home network. So the V2 router provides power over cable. I won't call it power over Ethernet. It's not really PoE. It's kind of a Starlink proprietary cable connector and power connection. The default configuration is only gives you Wi-Fi. You need to order a separate Ethernet cable adapter. Do it when you order your dish. because those were in short supply. The router provides DHCP dynamic addresses only in the 192.168.1.0/24 range. It doesn't support static addressing of your clients. It's only dynamic, and you have to take whatever address it hands out. It does seem to do a pretty good job of DHCP reservations, so it seems to remember your MAC addresses and hand out addresses. The dish itself responds to 192.168.100.1, and it provides performance, statistics, obstructions, configuration, so you can see what the antenna itself is seeing. Has it seen obstructions? You can bypass the Starlink home router with your own router. So you need the cell phone app. You can't do it on your local network. You have to bring up the cell phone app and tell it to go bypass mode, and then the Ethernet connection will allow you to plug your own router in, and its IPv4 router will turn off. When you do that, you assume responsibility for DHCP or static IP addresses, doing NAT, doing routing. You can provision VLANs if you want. You have to put in the firewall. You have to keep the Starlink router connected, but at that point in time, all it's doing is providing the internet connection from the dish to your home router and providing power, and all the rest of the functionality gets turned off. So I set that up, and 9 months ago, I ordered the kind of router I wanted, and don't try to buy a router right now. It's really difficult. It was on back order for 9 months, and then the supplier just outright canceled the order. So I'm off trying to find some other brand of router. Right now, the back order range is more than a year, depending on the kind of router that you want. They're dependent. It's the same thing as chip availability. There's some chip in there they can't get, and so the routers are very, very difficult to get. I've heard the name brand routers are out past 2 years back order delay, so routers are hard to get. So this chart is what I call a day in the life of a CGNAT packet. So let's look at what's going on here. CGNAT uses 100.64.0.0/10, which is an unroutable, not a publicly routable address block. So we have a Arden client over here on the left, Starlink internet connection, some public internet, and an Arden server node over here. So one of your computers that's the Arden client says, I want to talk on TCP port 5525 to my client, and it knows that it's at 138.27.63.105 TCP port 5525. That's a publicly reachable address. And it says it's coming from 192.168.1.106.5525. Your Starlink home router says, gee, I've got 256, up to 254 computers out here, and so I'm going to mangle the from address using source NAT, and so it'll come out of your home router as coming from 100.64.3.4.59.953. It goes over Starlink, hits the Starlink ground router, who's got 128, up to 128 different customers, and it says, okay, I have a public address at 98.97.112, and it's going to mangle that port number. It goes through the public internet and finally arrives at the Arden server node, and so it gets something to its public address from this twice natted address, and it knows how to reply. It just reverses the address and sends it back. The packet comes back, hits the Starlink ground, and this is the Starlink ground router knows that it had natted your port, and so it knows which home to send it to. That router knows that it natted the port, and the packet ends up getting back to where it started from, and the tunnel comes up and runs for a couple of minutes, or however often that this thing repeats. The return path knows how to get there. The problem is CGNAT table entries time out. For a Cisco router, the default timers for TCP are typically 120 seconds for the initial setup and 1,800 seconds for inactivity, about 30 minutes. So this client has to send keep alives more frequently than every 30 minutes to keep that tunnel up so that the server here can figure out how to send things back. If you use UDP, the default timers are 30 seconds for setup and about 120 seconds for inactivity. Starlink may use different timer values, I don't know. Those are the defaults on common Cisco routers. Once one of those entries times out, this server doesn't know how to find that client. So the client has to send another packet, then the server can figure it out. So if you were to put a server on a Starlink link, nobody anywhere would know how to get to that server because they wouldn't know its address, they wouldn't know what port number to use to get to that server. So the client tries to contact, but it doesn't know the address, it doesn't know the port number. So when Starlink provides internet to the server, the address and the port number does not resolve into a place that it can route to. Furthermore, because Starlink can have many thousands of computers on a single IP address, there are times when it has to be pretty aggressive about reclaiming idle port numbers. And I've seen it time out TC ports in 7 or 8 minutes occasionally during the busy hour, so your port number can time out fairly quickly. So it turns out that there are a fair number of wireless internet service providers that are also using CGNet, and they have all these same set of problems. So what do we do now? We need a way to know the public IPv4 address and port number of the server. And a couple of approaches. One is to use a virtual private network that both ends, the client and the server, can find and talk to, and the VPN has to externally resolve IPv4 ports, or we can use a cloud host to provide a public IPv4 and proxy the ports. There's a very good free VPN service called Tailscale. Tailscale is exceptionally easy to set up. The free plan is good. It gives you up to 20 hosts, 1 subnetwork router, and 1 management computer. Very little configuration setup is required. You pretty much turn it on, put the Tailscale client on the hosts you want, go to the management console and authorize them, and it comes up and works. It's an almost zero configuration setup. It's the easiest thing I've ever set up a VPN on. Tailscale does not know your encryption or decryption keys. All of your hosts have to set up their own keys, and Tailscale uses WireGuard on the host to do the encryption and decryption. So the end clients have to be responsible for their keys. Tailscale doesn't know that. So you install the Tailscale client on the hosts, and you go into the management web interface and you authorize each of those. Tailscale shows up as an additional Ethernet interface on the host. You might have ETH0, and when you turn it on, then you also get Tailscale 0 as a interface on your computer. Tailscale handles dynamically finding and logging where each VPN device is in IPv4 space. So your client dynamically links your address out to Tailscale's servers, and Tailscale servers in real time keep track of where all of the VPN endpoints are. They periodically send keep alive packets to keep those tunnels up. So those tunnels are encrypted, and so it gives you, for example, secure VPN access to your home network via Starlink. There are other providers. There's Cloudflare has a good free VPN package that can be used as well. Tailscale is the you can be a VPN dummy, and it comes up pretty easy. So what does Tailscale do? At home, you have a host computer. You install the client on it, and you get CGNATed through the internet. And so Tailscale's client periodically talks to Tailscale servers, which have a public IP address, and it can tell you where it is. They typically use port 443 HTTPS to talk to the server. They run a protocol called stun, and stun is a way for you to send a packet to the servers, and the servers can come back and say, here is the IP address and the IP port that that stun packet came from, so that you now know what your IP port and IP address is. Tailscale servers will tell you. Tailscale attempts to set up a tunnel on port 41641, a UDP 41641 packet, from endpoint to endpoint, so that your traffic does not actually transit the Tailscale servers. It's a point-to-point VPN network. That doesn't actually work on Starlink because you probably are not going to get that port number, and it's not going to resolve at both ends. So Tailscale will fall back and allow you to negotiate a TCP connection on what's called a digital end relay point for difficult CGNATs. So in this case, you now have this public server where all your VPN endpoints can show up in the database, and Tailscale will resolve all of that for you. Tailscale uses VPN tunneling. Tunneling encapsulates an entire IP packet, including the to from address field and the data field, with an outer UDP to from address field. So for example, the entire inner packet, we get a little confusing here. Tailscale uses the 100.64 address space for the VPN addresses, and Starlink uses the 100.64 address space, but they don't conflict with each other because the Tailscale assigns you a VPN address in the 100.64 range, puts it with your data, and then encrypts this entire packet, and then puts an outer routable address. And so even if the outer UDP address were to be the same as the inner address, it actually still works. So you can have overlapping address spaces. So your 100.64 address appears as an additional Ethernet interface on the host as Tailscale 0. Tailscale figures out what kind of a routable address to actually put onto the packet. You encrypt it, wrap it, and you send this outer routable thing, and you can't see any addressing or data inside. The VPN then generates these frequent keep alive packets. So when using a Starlink connected ARDN server, if the ARDN server and client are on the same VPN network, then they can talk to each other because they just see a single point-to-point tunnel. They're both on the same LAN. They communicate. If the Starlink connected ARDN server is not on the same VPN as the client, then the client can't reach the server, doesn't know the address, doesn't know how to get there. So in this case, to make publicly available services when using Starlink, we need a cloud host. And a cloud host is some way to get a publicly routable IPv4 and port numbers with static source NAT tables, so those statically mapped, and then get those crammed into a VPN and linked back to where you want to go. Once you solve that general problem, you can provide public services, a web page, SSH client tunnels, then that works with ARDN as well. So one of the features of Tailscale is that it provides what's called a subnet router. And I run Tailscale in a subnet router as a Docker container on a server at home. And Tailscale talks to that subnet router, and the subnet router can advertise an entire set of LAN ranges to Tailscale. This is very handy. For example, what if one of these devices on the LAN's a printer? You can't install the Tailscale client server or client software onto a printer, and so the subnet router will just handle routing that into Tailscale for you. And ARDN, you can't install the Tailscale client software on the ARDN node, so you let the subnet router do that for you, and you can control how many that you advertise. One of the difficulties is, you might want to do this where you have an ARDN node here and an ARDN node here. They can show up on the same subnet, so they all look like they're on the same subnet. The free plan gives you one subnet router. And if you need two, then you have to buy the Tailscale Personal Pro plan, which is $48 a year. But it would allow you to do that. So a number of companies provide what folks call rent-a-host. Linode, DigitalOcean, Vultr, there's a whole range of these folks. And they're typically in the $5 to $10 a month price range. And essentially what you get is a static IPv4 address for your host. And of course it has all of its own port numbers. You might also want to acquire a DNS name for about $10 a year and go push that out to DNS. You can install the Tailscale VPN client on that host, and you can install a reverse proxy on that host. And a couple of packages like Nginx or Traffic will receive a packet to a port number at a public IP address and then proxy that traffic over the VPN tunnel back to your home network and direct it to the computer that can handle that request. And Nginx and Traffic are open source. The VPN tunnel is fairly inexpensive. So the reverse proxy holds NAT tables of port number type to VPN network, client, IP, and port. And so it allows you to provide local services like a web page or an Arden tunnel server or SSH to a publicly known address. There is a service called Local Expose, so you can go to localexpose.com that bundles, that packages all of this for you, provides a hosted VPN and reverse proxy. They have a free package, which is exceptionally limited. It gives you 4 HTTP reverse proxy addresses, and that's it. Doesn't proxy UDP, doesn't proxy TCP, but it's free, allows you to essentially put a web page up and try it out. The $60 a year plan is more useful. It will allow you to proxy TCP and proxy UDP. So if you don't want to go through the difficulty of configuring a reverse proxy in a VPN, you can just buy it. There are folks who are using wireless IP services that are using CGNet that you can go on YouTube and just search for Local Expose, and there'll be some good videos on how to set it up, how to use it. And so it's a very convenient service. So the way that this works is you have a cloud host. You get this perhaps from Linode, let's say. You have a public IPv4. You install a VPN client. You install a reverse proxy. Now it's up to you. You've got to put a firewall on that. You will get attacked. You have to have a firewall. You do your own static NAT. And for example, you can proxy an incoming TCP 5525 over the VPN to your Arden server way the heck over here, and your clients now know how to find that server and they can talk to it. It doesn't have to be, it can be any service, but this works over Starlink. So the conclusion is Starlink provides a working Arden client tunnel out of the box. If you only are going to put the client on it, that client initiates the connection to the server can find it, and as long as it's sending keep alive packets frequently enough, the tunnel comes up. I've had good luck. I've had tunnels stay up for months. The keep alives are frequent enough. If Starlink reclaims the port I'm using, which it does sometimes, and I get a new IP address, then the client will recognize that, and when it times out, it'll send a new packet. The tunnel comes back up and reestablishes itself. Good reliability. It's been working well on our network. We put that in, and then since we've rebuilt the difficult paths with a couple of 5 gig point-to-point mountaintop links, and then we can go turn off the tunnel. If a station fails, we go turn the tunnel back on. We get to the node and reboot the node that's causing a problem or whatever it might be. So the tunnels can be very helpful. So it allows managing, reconfiguring, rebooting remote nodes. Try to have that server at a publicly reachable address if you can, because it avoids all of this cloud hosting and VPN issue. If you can't, and you have service to the server that's using Starlink or using some kind of a wireless internet service, then either get both ends on the same VPN, or you have to establish a cloud host and a reverse proxy to provide a way to get back to the service. We've been using this for 4 or 5 months now, and we've had actually pretty good luck with it. It's been more reliable than some of our RF links. So that's it for the presentation. Do we have time for questions?
Yes, you do.
Okay.
So is it turned on? Where's the switch? Right there. Push up. And the ramps. Okay, you turn it off.
Do I get to ask my question?
So, very interesting discussion. The Arden software is designed for rapid field deployment, automatic configuration. It's great for emergency services. The tunneling approach that you're taking is something that I do already, though I don't have Arden. But ARDC has 12 million addresses that can be used on VPNs that are routable IPv4, and that's what I do. I have a virtual host in a data center, and I send out IP addresses to a lot of different locations. I believe that WireGuard is part of the stack that's available for the routers that Arden supports.
Okay.
And if that was automatically put in and provisioned to go to servers that could be provisioned, you could cut out a lot of the cost and a lot of the complexity. Just my input.
Yeah, the Tailscale is, at least in the small plan, is a free service. And so we haven't run into the cost issues on that.
Yeah, John kind of beat me to it, but I was going to say I kind of know where you can get some publicly routable IPv4 addresses if you like. But no, in all seriousness, you need to get in touch with our technical advisory group. This is exactly the kind of thing we're discussing. We need to know what you need. And we also have money to fund this infrastructure. So right now we are discussing, we're trying to discuss exactly what kind of infrastructure we need to support this.
Okay.
Please come talk to us.
Okay, will do.
Yeah, and I'll just say, you know, the cost factor goes away because once we have VPN servers set up, then there's no plan that you have to pay for. So
Yeah, the VPN servers have so many VPNs have so many other applications besides Arden. You know, there's a lot of SDR radios that have to be on the same subnet as the controller, and if you have a VPN, you know, you can remote them and still be on the same subnet. Just so many applications.
I have run into issues running a VPN on Starlink.
Oh, you have?
Yeah. So, and it might be, do you have VPN on your phone? Do you run Tailscale on your phone?
No, I do not.
Okay. So when I have VPN running on my phone, my laptop, everything else. So when I fire up my Starlink, and I have the RV model to I can take around to places, and when I fire it up and then connect the Wi-Fi from my phone to via the app, the first thing it tells me is you have to disconnect from VPN to use Starlink. And the way it's worded is very ambiguous. It's like, hey, we don't allow this type of thing on our network. But I've never tried running. But once you get into the app and set it up and make sure you got a connection and et cetera, I've never tried running a VPN from my laptop on it. So I was wondering if you would run into that issue of VPN, like Starlink and VPN not seeming to like each other.
I just run the client in a Docker container
okay.
On a server so that it essentially handles proxying for every device
okay.
on the home network.
All right.
Yeah, I have a friend that has a mountaintop remote site in central Pennsylvania, and he's been trying to get Starlink to provide higher speed access than what he gets from a local phone company, and it sounds like it's going to be a little more complicated than just installing a Starlink.
Yeah, in the case of Arden, for example, if what's on the mountaintop is the client, it's plug and play. At least when I've used it at home, I haven't had to do anything. I just hook the internet, and the client is capable of bringing up the tunnel to the server automatically. It's when the server has to be on a CGNAT that you start to run into problems.
Any other questions? Okay, thank you very much. So what we're going to do is the break is set up. So you have the pretzels, popcorn, Cracker Jacks. I hope there's a prize inside. Good. And then we will get started at 2:50, 14:50.
We'll go ahead and I'm going to get started right at 3. So I gave everybody an extra 10 minutes. What it is, we have one talk by Bob McGuire that we never got. So we've got an extra. So what I'm going to do is I gave everybody 10, and then I'm going to do another 10. Oh, the introduction? Or I'm sorry, in the introductory session? Yes. So in the introductory session at 3:15, the introductory session starts. For Daryl Davis's basic microcontroller, is that the one? Okay, so if you're interested in attending the basic microcontroller interfacing techniques, it starts at 3:15. But I'm going to go ahead. What we have next, let's see, let's get George, or can you, is he? Okay. All set? Yeah, that's the presentation there. It's a video.
The camera's pointing at the screen, not at him. Yeah. Him. There's no presenter on this one. Right?
I'll introduce the talk, and then you're right. It goes right to the... George, you okay? Okay, and then Jason? Okay, and Gary. All right. Welcome back, everyone. Gave you an extra couple of minutes. We haven't received one of the recordings, so we've got kind of an extra 20 minutes there. I gave you extra 10 of those 20 minutes in that break, and I think it was well deserved. Everybody's having great conversations and having a contest to see how many miniature corn dogs they can eat. How was the snack? Good. Yeah, your choice of sugar or salt. I mean, the most basic of dietary requirements. The third one, of course, is caffeine. All right, so what we're going to do is we're going into 2 recorded talks. Each one of them is 20 minutes long, and both of these are submitted papers. They are published in the proceedings, and these are published, the authors and their presentation. The first one will be by Pete Lovell, AE5PL, and the topic is APRS-IS evolution.
Hello, I am Pete Lovell, AE5PL, and I will be presenting today on some new features that we've added to Java APRS server and therefore to the APRS-IS network. To do this, we need to review the APRS-IS evolution so that we understand why I took the processes that I did to make these new enhancements. APRS-IS is an ad hoc network. There is no controlling body, no controlling person or committee or group that owns and operates APRS-IS. It is independently owned and operated by, each server is independently owned and operated. Each gateway, each client, every radio station is an individual amateur radio operator that runs that device, that software, anywhere in the world. It is important to understand this, that even though that is the case, APRS-IS has survived for over 25 years of providing the amateur radio community an effective communications mechanism worldwide for all APRS users, whether they're on RF or on the internet. Java APRS server, of which I am the author, was introduced in 2003 to address the stability issues that we were seeing within APRS IS. Specifically, at that time, the servers on APRS IS, which was APRS Serve and APRSD, they were crashing within 24 hours every single day. And that just was presenting an extremely bad interaction for the amateur radio community. We needed something different. And so I went to work with the author of APRSD, Dale Hetherington, and we worked on coming up with a solution to the loop packets that were crashing the servers. In other words, they would just, you'd send out a packet and it was being echoed back, things like that. Bad packets crashing clients. The packets would be come in mangled off of RF, and they would continue to be mangled throughout APRS IS. Full feeds were crashing clients. For instance, WinAPRS couldn't handle more than 4,096 stations. Guess what? In 2003, there were far more than 4,096 stations that were showing up on APRS IS. Because of all the crashes, people were setting their APRSD servers, for instance. They were setting those up to have a feed to every single core server at that time. There were 3. They were setting it up so that there was going to be APRS connections to other Tier 2 servers. All those connections were causing overloads of the servers themselves. That, together with the loop packets, was causing even a worse situation. I chose Java because it was going to be used on multiple platforms, and I couldn't be supporting each platform individually. So it had to be platform independent. One of the keys too was that there could be no modification of data. We saw 2 types of modification, or actually 3 types of modifications of data at that time that was extremely prevalent. Number 1 was the stripping of nulls and or non-character data, non-ASCII data, for instance. Or what would fall into the world of control characters. We were seeing the modifications of MICD packets, because some of those packets also contained non-printable characters. We were seeing people taking MICD data packets and translating them into non-MICD packets. And again, this is partly because of the mangling of the MICD packets that we were seeing. People decided that it was better just to try to translate them at the eye gate. All of those types of modifications were being done, and Java APRS server said, no, we're not going to allow that, but we are going to be able to detect duplications. For instance, if somebody sends a MICD packet and it got translated, the translation might be blocked because it's considered a duplicate. We also couldn't deprecate any existing clients. So if they could connect to APRS IS at that time, they still would have to be able to be supported. Java APRS server had to be modular, capable of expansion, and because of that modularity, it was also maintainable. Since 2003, we've seen a number of new features in APRS IS. The Q algorithm, number one, was the biggest stabilization factor to the APRS IS network. And this was implemented between Dale and I in APRSD and Java APRS server. What this did was allowed us to use the non-data portion of the packets, which was the header, and we were able to say, okay, we can now detect some looping, and we can also do some tracing using that path header that was part of the TNC2 definition for command line viewing. I also added UDP support for non-directly connected co-resident UDP producers. What this did was allow login line to be included in the UDP packet so that you could use UDP remotely to the server. And this has been implemented in Java APRS server and was subsequently also implemented in APRSC. I also implemented HTTP support in Java APRS server, which would allow you to send APRS packets if you included in the post a login line. And that login line was a valid login line. APRSC also implemented this. Early on, Roger Billy came to me and asked if maybe we could add a filter to Java APRS server, which would allow the client to specify what they wanted to see from the APRS IS feed. And in fact, he did create that and is subsequently been always included in Java APRS server and subsequently within APRSC. The Java APRS filter production was probably the most significant for client authors because they could now say, okay, I'm not going to see the entire APRS IS feed. I'm only going to see a very limited subset. So I can spend my time handling mapping, messaging, things like that. And so it's a very important feature add that Roger did for us. We also have added services in APRS IS, those being CQ server, email, SMS gate, weatherbot, weather server, and there's lots of others. Some of those, like CQ server and email, are actually implemented as clients, integral clients into Java APRS server. I also, in early this last decade, added WebSocket support after it became a RFC standard, and that was to allow clients to be able to connect over wireless primarily, where HTTP connections and it might be considered to be less costly than a standard TCP connection. Because of this support for WebSockets, we've also needed now to add TLS support because browsers today that get a page via HTTPS cannot make non-secure WebSocket connections. They have to be secure. also in the process of doing that, I realized that we also needed to start to support the HTTP 1.1 authentication framework, which, by the way, is not necessarily security, but it is an authentication process that can be done via headers. And we also needed to clean up the rest of the HTTP header and response operations. For TLS support, we required a new port to do that because you cannot have both a TLS and non-TLS connection on the same port. The TLS support for WebSockets meant that we also support for all HTTP. And TLS is an evolving protocol. In other words, we're currently at 1.2 and 1.3, and 1.4 is not been certified yet, but it is in development. So we needed to be able to support that as time goes on. And also ciphers. There's been a lot of TLS 1.2 ciphers that are considered no longer secure that needed to be blocked. I also realized that in Java APRS server, we needed to be able to not only support the server port, but we also needed to be able to support making upstream connections using TLS. Currently, the TLS support in Java APRS server is 1.2 and 1.3. The supported ciphers in 1.2 are shown there. Basically, we took out the CBC ciphers and the SHA1 ciphers, basically, the RSA ciphers. Some of these ciphers may not be supported by the platform. For instance, Android does not support all these ciphers. And so the implementation uses this list as this is the maximum number of ciphers and the maximum ciphers that can be used. But if the platform supports less, then the subset will be used. Same thing for the TLS 1.3 ciphers. This is all defined in a properties file, a text file. And so therefore, as new things get added, as new ciphers get added, as new protocols get added, those protocols can be supported in a standalone properties file without modification of Java APRS server. The HTTP 1.1 authentication framework is defined in RFC 7235. And specifically, it says that the server generating a 401 response must send a www authenticate header field containing at least one challenge applicable to the target resource. Bottom line is neither APRSC nor Java APRS server was doing this. So when I took a look at it, I also looked at how other authentication mechanisms that are defined in the standard were using it. And one of the things I saw is that basic authentication, which has been around since the earth cooled, uses base 64 to encode the username and password in the authorization request header. This is very important because this is what I took to say, okay, if we're going to support it, the easiest way to support it is to use that base 64 encoding. So first of all, within Java APRS server, we added to the 401 response code a www authenticate response header, which the type is APRS-IS, which is allowed by the RFC. And the realm is supposed to be some helpful text, so the actual header generated by Java APRS server is APRS-IS as the type, and the realm is APRS-IS valid login. Now, how does that translate to the user, to the client? The client is going to use the authorization header, which will still have the type of APRS-IS, but also have the base 64 encoded login line. By using base 64, very little needs to change in the server code or the client code. Basically, all we're doing is encoding an already generated login line. What is not included is the carriage return line feed of the login line. So basically, this is the login line sans the carriage return line feed. However, when I did base 64 encoding, it could happen on all ports, not just HTTP ports, because all we need to do is detect the encoding of the login line and say, okay, we need to decode it. Base 64 libraries are commonly available all around, and base 64, as it important to note, is not secure unless used within TLS connections. So basically, APRS-IS continues to evolve. It is evolution, not revolution. All prior clients still supported. TLS support for today and tomorrow. So in other words, all it takes is changing this text file to be able to add protocols, add ciphers, delete protocols, delete ciphers. And HTTP 1.1 authentication implementation allows base 64 encoding of all login lines, not just within the authorization header of HTTP. Finally, again, I am Pete Lovell. I've been a ham since 1971. I've been using AX25 since 1987, APRS since about 1997. I have been professionally involved with computers and networks since the 1970s. That is what my degree is in, is computer science. I obtained my CISSP in 2006. CISSP is a certified information systems security professional. It is a very difficult certification to obtain, and I mention it here because the topics were regarding security, TLS. Base 64, whether that's secure or not secure, things like that. I am not ignorant of security. I am very familiar and been very deeply involved with security for many, many years. And base 64 is not secure. However, base 64 encoding is very simple to implement, meets the standards, and can be secure if carried over a secure connection. My websites are ae5pl.net, aprsis.net, jfindyou.net, and ax25.net. I can be reached at pete@ae5pl.net. Thank you very much, and have a great day. Enjoy the rest of DCC.
Big round of applause. So thank you, Pete. So while that was, go ahead.
I just want to say the point he was making is base 64.
Hold on. Whoa.
Sorry. Base 64 is an encoding like ASCII. It is not encryption. It is the simple statement of his point there.
Good day. My aim today is...
Okay, so I thought I had it on. Next one up. This is Gwen Griffiths, G3ZIL and et al. There were several people on the authoring of the paper that, again, is in the proceedings. And this is titled FST4W on the HF bands. Why, what to expect, equipment, and results.
Good day. My aim today is to show you that FST4W, a digital protocol akin to Whisper, is of real value on the HF bands and isn't just useful at LF and MF. All co-authors have made substantive contributions to gathering the information to show you today,
and we are grateful to our collaborators acknowledged here for their enthusiastic assistance. Why bother with FST4W? Well, there's the nice to haves. A decode threshold about 1.4 dB lower than Whisper for the 122nd variant, and the longer variants have even lower detection thresholds. FST4W also has greater tolerance to Doppler spread, decoding at 7 dB lower SNR than Whisper at 2 Hz Doppler. But there are downsides. If using WSJTX, you have to set one sequence length to listen for. Admittedly, there is a technical challenge. There's no drift compensation, as in Whisper. And as sequence lengths increase, the requirements on equipment spectral spread become even more challenging at HF. The waterfall on the right from N6GN shows a real FST4W120 transmission at its 33rd harmonic. Now, smearing from one tone frequency to another because of either equipment or ionospheric spread can set a limit to the mode's usefulness. It is understandable that these downsides mean few people are using the mode today. But, as we'll show, each of those downsides provides a challenge that we are already overcoming. But here's the game changer for why FST4W at HF deserves more attention. It measures spectral width, although not by default, and it's a little tricky to turn on. This means FST4W gives you the critical tool to counter the downside of spectral spread, whether from equipment or the ionosphere. In the graph of decode threshold versus spectral spread for FST4W120 and Whisper here on the right, I've shown two regions where spots are unlikely to be decoded. Here, if the SNR is too low, and here, top right, if the spectral spread is too large. But it's often not clear with Whisper which of those two situations pertains. But with FST4W, we can ascertain which of those two limits is at play. On first thought, it's almost unbelievable that this 900-second FST4W transmission from Fort Collins to Santa Rosa was not decoded. But it wasn't. Too much spectral spreading, despite the very high SNR. And the final why, once we have backed off equipment spectral spread, the remaining spread from the ionosphere may be of interest to the science community. As to what to expect, here's an example time series of SNR in the top panel for FST4W120 transmissions from Fort Collins to Maui. As in all the examples today, the transmitter uses a phase-locked GPS-DO. Keeping one variable fixed is of great help. Here, the receiver is a standard Kiwi SDR, with its out-of-the-box GPS frequency aiding before we'd uncovered a bug that now should give improved results. The bottom panel is the game changer. A histogram of spectral width of the decoded spots. We'll show later how to split this out to contributions from the transmitter, the receiver, and the ionosphere. Getting a feel for what to expect is made easier using the FST4 SIM program that comes bundled with WSJTX. Given this set of parameters, the FST4 SIM generates the specified number of WAV files that one then decodes with a JT9 executable. Here we've kept all variables fixed except for FDOP, generating 50 WAV files at each value of FDOP and plotting the results. Importantly, we need to keep in mind that FDOP is the total spread from transmitter, receiver, and the ionosphere, and so we've labeled here as spectral spread. From 50 runs at each FDOP, we get the decode probability with spectral spread in red, what FST4W considers the spectral width in green, and the output SNR in purple. The output SNR decreases with spectral spread as energy from one tone band leaks to another. Decode probability reduces because we're not decoding those with greater spectral spread. So we get a biased spectral width that becomes increasingly biased low as the spectral spread increases. The data should, this green line should really follow all the way up here. For reference, the results from the last slide were within the grey box. So they were comfortably within the usable range for FST4W120. We can also use FST4Sim to estimate performance at one sequence length, say 900 seconds, where we have a spot count and spectral width data for a shorter sequence, say 300 seconds. In orange is the histogram of spectral widths from 14 MHz FST4W300 transmissions from Fort Collins to Maui. Its right-hand tail here is curtailed. It extends into the region of reduced probability of decode from the solid red curve. But look at the decode probability curve for FST4W900. When we multiply that curve by the data in the orange curve, we end up with the brown distribution, which is the estimated number of counts of decode with spectral width for FST4-900 between Fort Collins and Maui. Just 98 out of 431 spots of the orange curve would be detected and decoded for 900-second transmissions. In fact, the results were even poorer. Only 8 were decoded in a 2-day period. Let's move to equipment. Given what we've just seen, it's not surprising that early tests with FST4W on the HF bands were disappointing. Kenji JJ1BDX has kindly allowed me to share his graph and experience. He could only get his own FST4W300 transmissions to decode at no higher than 3.5 MHz, and that's without any additional ionospheric spread. The drift on his FT891 was just too large on transmit. It's fine on whisper when linear drift is removed, but not on FST4W. The receive side of commercial transceivers can also be problematic. Temperature rise on a transmit cycle may result in excessive frequency drift in the following receive cycle as the TCXO gets back into being stable. And that may take several cycles to stabilize sufficiently to be able to decode FST4W. So what equipment does work? All 3 transmit stations in this study used variants of Anand software-defined transceivers with phase-locked GPS DOs. These performed excellently. We have made an initial study of the remarkable $69 QRP Labs QDX digital modes transceiver, but its novel single signal generation method results in too much spectral spread in its current implementation. It's fine on receive. Kiwi SDRs have provided the vast majority of spot data for this study, about 50-50 between those with out-of-the-box GPS aiding and external phase-locked GPS DOs. And an LAD FM duo with GPS DO has also worked excellently in this study. Here's how we've got rid of a major impediment to uptake on receive. Rob Robinette's Whisper Daemon version 3 allows the Kiwi SDR user to declare which modes from whisper to all of the FST4W lengths to decode for each receiver and each band. By recording 1-minute WAV files and concatenating as needed to present to the whispered and JT9 decoders, only one Kiwi receive channel is needed to decode all these modes on one band simultaneously. That's a big step forward to the one-at-a-time approach with WS-JTX. Moreover, Rob switches on the measurement of spectral width and logs the data, and is working on extracting the 1/10 of a hertz frequency resolution that FST4W can also optionally provide. Moving to results, let's compare how many spots with SNR at or lower than -30 dB were decoded by QESDRs with standard frequency aiding and those with phase-locked GPSDOs. Remembering that for decoding at the lowest SNR, we need low spectral spread. Or should we not bother? Might not the ionosphere spread dominate? Well, not on the 1,500 kilometer path from Fort Collins to the Bay Area. For FST4W300, a test for no difference was rejected. QESDRs with GPSDOs won hands down in this test on 7 MHz. It wasn't down to the antennas or location. The GPSDO receivers were in urban or suburban settings, while KFS and KPH, with their excellent antennas and low noise sites, just had standard aiding. This is how we've gone about ascribing spectral spread to receiver, transmitter, and path. In outline, we started with a GPSDO transmitter and receiver pair, 21 kilometers apart over a line-of-sight path. We gathered FST4W300 spectral widths, that's in the histogram at the top right, and fitted a gamma distribution. Gamma, because it is positive only and copes with the extended right tails, which is what we've seen on virtually each record. And the gamma fit is in red. If we assume no spread over the line-of-sight path, and as we had identical GPSDOs at both ends, we ascribed the measured spread 50-50 to the receiver and transmitter. We can do this by halving the gamma distribution shape factor, keeping its scale factor constant. Now we have the parameters to generate numerical simulations of the spectral spread of GPSDO transmitters and receivers individually. That's in the middle histogram. Next was an experiment over a 38-kilometer path between a GPSDO transmitter and a standard QESDR receiver. We again gathered spectral width data, formed a histogram, and fitted a gamma distribution. And from those parameters, we generated a numerical simulation. Then we make the perhaps contestable assumption of no spread over that 38-kilometer path. But then what we do is to subtract spot by spot the numerical simulation of the GPSDO transmitter spread from the total spread to arrive at a gamma distribution for the SDR spread alone. And that's in bottom right, just over an order of magnitude greater than that of a GPSDO. Having estimates of spectral width from a GPSDO transmitter and the GPSDO and QESDR receivers, we can subtract their contributions from the measured spectral widths of example propagation paths to get an estimate of the ionosphere-only contribution. This is perhaps where it becomes of interest to science. All three examples here are on 14 megahertz, FST4W120 from Fort Collins to Santa Rosa in the top, Maui in the middle, and New Zealand in the bottom panel. So not only is FST4W120 capable of global paths on 14 megahertz, it adds this entirely new set of measurements compared with WISPR. Over the path to New Zealand, there's not much to choose between a gamma fit in red and a Gaussian in blue. One of the few equivalent Doppler spread histograms that we found in the open literature is on the right. Across the auroral oval, note that the long tail was well suited to a gamma distribution. Moving from histograms to time series and to comparing two bands, we see a great deal that we as radio amateurs just don't understand. The three panels on the left are for 7 MHz, FST4W120, and those on the right for 14 MHz, FST4W300. The top panel is SNR, much as in Whisper. The middle panel is spectral width, and the bottom panel is the rate of change of spectral width with time. First, the spectral width behavior on 7 MHz was quite different to 14 MHz. Why? We have no idea. If anything, the geomagnetic conditions were somewhat more disturbed during the 14 MHz trials. Second, note that the spectral width on 14 MHz on 6th of September was essentially constant over an SNR change of 30 dB. That surprised us. Third, equally surprising, were the large changes in spectral width on 7 MHz between measurements just 4 minutes apart, except for an hour or two around 0700 UTC. That's about local midnight at the midpoint of the path between Fort Collins and Santa Rosa. But even then, the magnitude and variation of the spectral spreading was greater than those observations on the right at 14 MHz. Recognizing there is still a great deal for us to understand, here is a graphic that tries to give a quick look assessment of FST4W on 14 MHz based on our results. There's a plot for each sequence length and a color code for likelihood of decoding spots. Both X and Y axes are spectral widths, from example paths on the Y-axis and from different transmitter-receiver combinations on the X. FST4W1800 is only usable on 14 MHz over line-of-sight paths and with GPS DOs each end. FST4W900 over one-hop paths is feasible, but only likely with a GPS DO transmitter and a receiver with narrower spectral spread than a Kiwi. For FST4W300, as we saw from Fort Collins to Maui, with a Kiwi SDR, decodes were possible, but much reduced. With a receiver with lower spectral spread, the decode probability would improve, but global paths are unlikely whatever the receiver transmitter. FST4W120 is almost whisper-like. Just be sure that neither your transmitter or receiver drifts. As we've shown, global paths are readily achievable. Finally, FST4W is not just useful at LF and HF. It is entirely practical on the HF bands with readily available equipment. However, it does need care to minimize frequency drift and spectral spread of transmitters and receivers. We've shown tangible benefits of GPS DO receivers in decoding spots with low SNR. Most importantly, it adds a new variable to measure, spectral width. We've suggested a method to separate out the spectral widths of transmitters from receivers and the propagation path. After doing so, we've seen intriguing patterns in spectral widths worthy of further study. We've further work to do on characterizing spectral width following changes to the Kiwi SDR and are in conversation with QRP Labs about the spectral width of the QDX transceiver on transmit. Personally, I'd like to understand the mode's rather curious SNR algorithm, and there are endless possibilities to study SNR and spectral widths over interesting propagation paths. Do give FST4W a try. Thank you.
And a big round of applause. So thank you, Gwen, for the paper and the proceedings and your recording. Okay, John Ackerman, Come on up. Do you want the lavalier? They work better in your in your nose. There's a nose version that you can. Okay. Gary, you ready? Okay. Jason? Okay. And we're good. Great. Thank you very much. Okay. Next up, John Ackerman, N8UR, GPS modules as RF signal sources, possibilities and pitfalls.
Oh, good afternoon. Steve doesn't like me very much, so he always puts me at the end of the second day. And I'm used to it. Over the last couple of years, I've been doing a lot of work with GPS modules, particularly the ones from u-blox. And there is some new capability that these modules have that we're taking advantage of in a couple of TAPR projects, and I've seen some indication on the internet of other people thinking about using this. So I thought I'd talk about the results of some testing that we've done, what that leads to as some interesting ideas, but also some of the things that you need to be careful of if you want to try to take advantage of the advertised capabilities of some of these new units. So I'm mainly talking today about GPS modules, not the consumer handheld type devices, and in particular the ones that have a pulse per second output. And the old ones, you typically have an RS-232 that would carry serial data, and there would also be a single pulse per second signal. And that pulse per second can be incredibly accurate. It's very easy with a modern receiver to get within 100 nanoseconds of UTC time. And that's just kind of an astounding level of accuracy to be able to reproduce in your hand. But the older receivers had limitations. They were power hungry, and they didn't offer a lot of flexibility. They had enough trouble doing pulse per second and sending some NMEA data. The modern modules are much, much more capable. And in particular, they have pulse per second, or what we actually today call time pulse outputs, that are not just PPS, but they can go to several megahertz. And you know, that provides some interesting possibilities. There are also sometimes multiple outputs of both the time pulse and other signals available, more data paths available, just all sorts of cool stuff. Okay. And for example, the u-blox ZF9T, it's admittedly an expensive unit. It's just under $200 in single quantity, but the capabilities used to cost several $1,000s with dual frequency, which means it can compensate for ionospheric variation. It has 4 data interfaces that can send and receive different data streams. 2 independent time pulse outputs that can go anywhere from 1/4 of a hertz to 25 megahertz in rate, and raw code outputs and all sorts of other things. Again, that's an expensive version, but even the $27 version of the u-blox receiver, the NEO-M9, has 2 time pulse outputs that'll go to 10 megahertz. So even a very inexpensive receiver has that capability. Now, before we go further, I want you to take a look at this and keep it in the back of your mind, because it's the reference point for going forward. A traditional GPS disciplined oscillator is a phase lock loop that locks a crystal oscillator to that GPS pulse per second. You typically have an oven-controlled oscillator that's nice and stable. It doesn't have much jitter in the short term. You divide that down digitally to get to a pulse per second. You feed the pulse per second in from the GPS into a mixer or a phase detector, and you take that output, put a low-pass filter on it so that you smooth out the noise, and then you use that to control the frequency of the oscillator, steering it so that the oscillator, which is very quiet in the short term, is being controlled in the long-term frequency accuracy by the GPS signal that's very noisy in the short term. And typically, GPS DOs have done this with this detection at pulse per second, and a loop time constant that's usually 100 to 1,000 seconds so that you can really take advantage of a good oscillator to smooth out and get rid of that noise. So if I can get a 25 megahertz output from a GPS module, can I do this a little bit differently? And more interestingly, can I just use that as a frequency standard? Can I program it, say, to 10 megahertz? It is locked to GPS, and it's a good idea, but there is a significant limitation for hams in particular. That's what I'll be talking about for the next few minutes. That gotcha mainly comes from the fact that whatever the time pulse frequency that you program, the GPS engine is usually doing an update of the navigation and time solution once per second. In between those once per second adjustments to keep the oscillator of the GPS lined up with the GPS signal, the clock is free running. It might be running at 40 to 80 megahertz in a modern receiver. So during that second period, it's drifting around. It's not a very good clock. To keep the timing correct from second to second, the receiver will add or drop pulses to the output stream. So if you've programmed 10 megahertz, you get a pulse every 100 nanoseconds most of the time. On average, you will get a pulse every 100 nanoseconds over a long period, but within a second, or even much more often than that, there may be pulses added or dropped, and that creates transients which result in glitches that cause RF problems. So to summarize it, the time pulse long-term accuracy, stability, and its accuracy are really excellent. And it's interesting, I don't know exactly why, but if you look at the stability, how much the time information jumps around from second to second, it looks like the 10 megahertz, say, output is actually a little bit more stable than the pulse per second. I have a couple of thoughts of why that might be the case, but they're guesses, so I won't go into them. But the point is, for a long-term basis, that 10 megahertz time pulse can be very, very useful. But the phase noise that's on it is a real problem for doing an RF application. And by the way, hams, RF types, we talk about phase noise polluting a signal. Digital folks talk about jitter. The two terms mean more or less the same thing, but you have to be careful because they're specified and measured very differently. The jitter is usually integrated over some bandwidth, where the phase noise we look at specific offsets from the carrier frequency. So they result in the same thing, but the numbers are very different, and particularly for jitter, if you don't know how it was measured, what the bandwidth was, and some of the other factors, you can get numbers that are fairly meaningless, and the manufacturers take full advantage of that. So what is phase noise? It's unwanted modulation of a carrier, and it can extend out to hundreds of kilohertz away from the carrier. It's usually highest close to the carrier, and in theory, if you were able to get infinitely close to the carrier, it would be at the smallest discernible difference from the carrier amplitude itself. But it will tend to decrease over time, typically in some kind of a log fashion, depending on the type of noise, 10, 20, or 30 dB per decade. And in addition to this general noise, there often are spurious signals at discrete frequencies that can be much, much stronger. A very classic example of that in any oscillator is if you look at an AC-powered oscillator and look at 60 hertz and 120 hertz away, you will very often see sidebands from the power mains, or if you're outside the US at 50 or 100 hertz away. So those spurious signals can be there, and since they're a lot of energy at a single frequency, they can cause significant problems. So phase noise becomes an application for a problem for RF applications because it reduces the signal to noise ratio. You're taking the energy that you have and spreading it out over a wider bandwidth. It also makes it hard to do digital demodulation because it's hard to detect the bit edges. It can cause intermodulation distortion because you have these additional signals that are mixing with each other. And this can happen both far away. For example, a single sideband transmitter with a lot of phase noise can mix with another strong signal and create products quite a distance away. It can also be a problem within the signal. If you're doing a digital modulation that has 8 or 16 or 64 carriers, the mixing between those carriers can be a problem, and phase noise will result in a higher noise floor between the carriers. So it makes digital demodulation harder, and it also can create intermodulation distortion even in amplitude modes. And if it's bad enough, it can just make the audio get muddy and sound pretty bad. You typically don't hear it unless you get to very high frequencies where the phase noise is multiplied to be quite high. And this partially got cut off, I'm sorry, but it's important to note that the phase noise multiplies with frequency. If you have a frequency at 5 megahertz and measure how much power there is 100 hertz from the carrier, and then you multiply that to 10 megahertz, the noise at that same offset will be 6 dB higher. If you multiply by 10, it's 20 dB higher. So if you are starting at 10 megahertz and multiplying to 10 gigahertz, you have a tremendous increase in phase noise. And that's a challenge of microwave communication. You have to design frequency generation systems that can minimize the increase in the phase noise. So we can see this, and particularly why the GPS module doesn't work, by looking at some pictures. And for most of you, I think a spectrum analyzer display is something that you're familiar with. So I'll start with that. The two plots here, on the left is a span of 500 kilohertz from the, with a carrier in the center. The green trace is the output from a pretty good quality HP signal generator at 10 megahertz. The black trace is the output from the ZF9T GPS module with its time pulse set to 10 megahertz. You will notice a slight difference. That's 10 dB per division. So you can see that the wideband noise power is 10, 25 dB higher even at the edge of the screen. The right-hand slot is looking at 1 kilohertz, and here you can see the individual sidebands, the spurious signals that result from whatever digital magic is going on inside the chip that's being translated to the RF output. So within a narrow bandwidth, you have lots of possible interference sources, and these are signals that you just don't want to put on the air. They're going to cause your friends and increasing number of enemies a lot of problems because of the wideband as well as specific spot noise that they create. Looking at this in another way, this is a phase noise plot, and you can think of it as being that spectrum analyzer looking only at one sideband with the carrier at the extreme left edge. But it's a very narrow span and it's logarithmic, so it starts out at 1/10 of a hertz away from the carrier and goes out to 1 megahertz in decade steps. And here, I'm sorry I don't have precise apple-to-apple comparisons in these charts because I've taken lots of data in lots of different configurations. But here is that same ZF9T, 10 megahertz in the blue trace, and you can see there's a lot of noise that does come down decade for decade, but then from about 100 hertz on out to about 3 kilohertz, there are some really big spikes, and there are lots of spikes, and finally the spurs go away, but it still is pretty darn noisy when you get more than 100 kilohertz away from the carrier. So yeah, that's not bad, or sorry, that's not good at all. The violet trace is a Thunderbolt GPS-DO, which is one of the more highly regarded ones that have been very popular in the time nuts and to some extent the ham community. And you can see it still has some spurs and it's not perfect, but the difference between the two is, I think, pretty noticeable. So the GPS output versus a GPS-DO is significant in terms of the noise pollution. Now, this is simply meant to make you go, whoa. Same GPS module, looking at its program to generate different output frequencies from 2.048 to 20.48 megahertz. Actually, the bottom two are from a different receiver, although the results are similar. And the point here is that depending on the output frequency that you choose, the spectrum looks quite different. Some of this is due to that 6 dB per multiplication factor, but if you just look at the spurious pattern, it's really very different depending on the frequency. After a lot of testing, I can tell you that there's not a magic frequency. There are some reports out on the net that if you programmed one of these modules to 8.192 megahertz, it's clean there. And the reality is they're all bad, they're just bad differently. So you really can never consider this as an RF source because of the noise and the spurs. And sometimes it's worse than others. I found when I looked at integer megahertz outputs, 5 megahertz, 6, 10, whatever, that tended to be a lot worse than if I did multiples of 1024 kilohertz. And that's certainly due to the digital activity that's going on within the chip. I don't know what it's doing, but there obviously are some output frequencies that are synchronous with something that's happening in the receiver and causing it to get better or worse. And also there's a wide range of levels of spurs. So can we get rid of this? Well, think about a low-pass filter on an audio signal. If you narrow the bandwidth and cut off the high frequency, or to get rid of the hiss, you're reducing the high frequency component. You can reduce the noise on an RF carrier similarly with a narrow filter. CW filter on your radio versus the wider sideband filter. The problem is that to clean up a GPS output like we've looked at, you need a really, really, really narrow filter, way less than 1 hertz, to get rid of the noise. And that's not easy to implement simply as a filter. But the solution to that is using a phase lock loop. And that's a feedback circuit. And think back to that GPS-DO block diagram that I showed. That is a phase lock loop where it's steering one signal to be in phase with the other. A phase lock loop has the property of filtering noise that's further out than the bandwidth of the filter that's in that loop. So we can use a narrow bandwidth PLL to eliminate the jitter and the noise that's on the input signal and use the clean output from the crystal oscillator and get the best of both worlds. In theory, we have the stability and phase noise of the good crystal oscillator, but over a time period, it's steered to follow the GPS, which is very accurate frequency and is very stable over time. You need to be a little bit careful to match the bandwidth to the relative noise and the quality of the two oscillators, the reference and the crystal oscillator, because you want to look for the place where the noises cross over, where the point where the GPS noise is getting better the longer you integrate it, and the point where the crystal oscillator noise is getting worse because it starts to drift. And there's an intercept point there, and you kind of want the filter to be operating in that area. And typically in a GPS-DO, the filter ends up being something between 1 hertz or to about 1 millihertz. And with that kind of bandwidth, it's easier to think about perhaps time constants. So the time constant of an RC filter, that's just the inverse of the bandwidth. And so a 1 hertz filter has a time constant of 1 second. 1 millihertz filter has a time constant of 1,000 seconds. And that makes it a little bit easier to map what's going on in these devices, I think, than talking about the bandwidth. So what? Again, think back to that GPS-DO block diagram. you've got to take the 10 megahertz signal and you've got to divide it to pulse per second, and you've got to design a phase detector that can look at those two signals, and then you've got to get a voltage out of that, and you have to filter it, and then you've got to make it match the frequency sensitivity of the electronic frequency control of the oscillator. It's a lot of work. Well, in digital communications, there are requirements for the engineering systems that can sort of do a similar thing. In particular, you often have a master clock at some frequency, perhaps 40 point something megahertz or whatever, and they pipe that around to multiple boards and multiple racks, and it picks up a lot of noise along the way. And you need to clean that signal up on the input to the various processes that the thing's running. To address that, the industry has created things that are called jitter attenuator chips. And they're designed to take an RF clock signal coming in that may be all dirty and ugly and clean it up and give you a nice, very low phase noise, low jitter signal at the output. And they also often have the interesting additional capability of doing frequency synthesis. So you can send one master clock frequency around and then generate on each board exactly what frequencies you need for that board. So if you think about it doing all that stuff, it starts to sound kind of like a GPSDO. Here's a block diagram of one of these chips. It's the Silicon Labs, which is now actually Skylab, I think, or Skywave or something like that, jitter attenuator chip, which is designed to do what I just described. You give it an input clock signal, and it has a either crystal oscillator or an external oscillator like a TCXO, a temperature-controlled oscillator, connected to it, and it locks that oscillator to the input signal, and then through various kinds of dividers and multipliers can generate up to 10 different output frequencies, anywhere from about 100 hertz up to over a gigahertz. This is all done in a little 48-pin quad pack chip that costs about $18. So it's kind of interesting. In the red box here is the PLL, and it's all done digitally, of course. But there's a phase detector, a low-pass filter, a divider, an oscillator that's controlled from that, a divider, comparator, and it's doing all the things that a phase-locked loop does digitally and in a way that can generate discrete frequencies throughout a very broad range. It has some capabilities that GPS DOs also have. There's a thing called holdover, which is how well the output will remain on frequency if the GPS signal goes away. And the most clever of the GPS DOs actually learn the aging rate and perhaps the temperature coefficient of the crystal. And if the GPS goes away, they'll keep adjusting the frequency over time to keep the frequency closer than it would be if the oscillator were just free running. This thing has the ability to do that over at least a period of 10 or so seconds. So if there's a brief glitch in the GPS signal, it'll ignore it. So there's a little bit of capability there for the same type of thing that a GPSDO does. One limitation is that the bandwidth of the PLL is more limited. The chip that we're looking at here has a narrowest bandwidth of nominally 100 millihertz, or a 10-second time constant. So that's a limiting factor. They're really designed to work with cleaner signals and use a faster, a wider filter, shorter time constant to pass the characteristics of the input signal through. They're not designed for the GPS application, but the 100 millihertz filter, remember I said we typically use something between 1 hertz and a millihertz, so that's in the ballpark. So the blue line again is that ZF9T GPS module, just the raw output. The other two lines here are that jitter attenuator chip being fed by the ZF9T time pulse output, and different bandwidths of the loop filter in the digital PLL. So the blue trace is the horrible, ugly one. The violet trace is with a 1 hertz bandwidth. The green trace is with the nominal 100 millihertz bandwidth. So you can see the narrower the bandwidth, the more the noise goes away, and the more the noise floor drops. And when you get down to looking at this green trace, it's not too horrible. This is also being measured at 122 megahertz. So that multiply 20 dB for 10 dB 10 times multiplications playing into the absolute numbers. So kind of ignore the scale on the left, but just looking at the curve, we start to get quite a nice looking signal. This was all done on a breadboard that I'll show you in a minute. And some of the spurs that you see in all 3 signals, I think, are due to noise in the lash up. So in a production system with everything integrated, I'm hoping that some of those spurs will go away. So now this is the same thing, looking at kind of an optimum form, at this time at 10 megahertz. So it's a little bit more typical of what you might see in a measurement. And again, we see a lot of improvement. There still are a couple of spurs. The worst of them, though, is still about 70 dB down. And again, I think those may be measurement artifacts. So this jitter attenuator chip seems to be able to do a pretty good job cleaning up the GPS RF output. So the Tangerine SDR needs a GPSDO. Scotty talked about that yesterday. And the original implementation that we had looked very much like that traditional one that you saw at the beginning of the presentation. Our output frequency for the clock and the receiver is at 122.88 megahertz, so we needed some kind of synthesizer in addition to just the 10 megs. So this is what we ended up with after kind of discovering what's been in the previous slides. A GPS module here, it's that expensive ZF9T, but you can use a much cheaper one. Its time pulse output is set to an RF frequency, goes into the jitter attenuator chip. There's a 50 megahertz TCXO that's locked to the GPS signal. And then you have up to 10 outputs, and we're using one of them at 122.88, but the others can be lots of other different things. We also get pulse per second out of the GPS module, and there's other capabilities. But we've reduced the entire GPSDO and the synthesizer down to basically 2 packages. There's a little bit of other stuff. But it becomes very simple, and it gives us everything that we need. This is the clock module. I think Scotty showed a picture of this yesterday. I did not lay this board out. I wish I were skilled enough to have done it. But this is a 6-layer board, 40 millimeters square, more or less. The GPS module is on the bottom, this is the top side in the right-hand picture. The synthesizer is the jitter attenuator chip synthesizer is the large chip in the middle, and then there's a little bit of other stuff. The TCXO is, I think, right here. The crystal oscillator, the temperature compensated oscillator, is 5 by 3.2 millimeters. Because we didn't have a lot of room to work with, so it's 50 megahertz and very, very, very small. The connectors, Scotty already mentioned, we're using this M.2 connector. It's the same thing that solid-state drives use. It's sort of an edge connector on the board. And what's nice about it is that it's very, very cheap, but it's rated for gigahertz speeds. So we can pass the high-frequency clocks through it. This board will plug into the Tangerine SDR, and actually it plugs into the data engine board, and then the RF module and the VLF modules can use the signals from it. We have the multiple outputs available that are largely independently programmable to whatever frequency you want. There are a few limits of the relationship between the frequencies. We get the pulse per second directly from the GPS module. But we can use the system without a GPS by feeding an external oscillator into it if you need better performance than we can provide with the GPS signal. We have multiple performance levels. The basic one is no GPS module at all. You feed in 10 megahertz and it just synthesizes to give you what you need at the output. Then, because marketing is cool, we have the gold, silver, and bronze performance level versions that go from using that ZF9T, $190, $160 if you buy 250 of them. Then the silver is a timing receiver, but it's the single frequency. It's $84. It's actually gone up very dramatically since we first priced this in 2020. U-Blocks is trying to, I think, tell people not to use it. It used to be like 50 something, and now it's 84 in 250. And then finally, the cheap one is the Neo M9N. That's $15 if you buy 250 of them, $27 if you buy one. And we originally thought that using that cheapest one, we could get the RF output, but we would lose the pulse per second because the cheap one is not documented to have 2 time pulse outputs. Well, guess what? It does. There's a pin on there that says that it's reserved in the data sheet, but it's the time pulse 2 output. So using this cheapest GPS, we can still get all the functionality that we get from the more expensive one. The performance isn't as good, but it gives you a very low-cost entry point for getting a GPS-disciplined oscillator. This is the lash-up that I showed you before. The big blue box, or the big blue board, is the jitter attenuator evaluation board. The thingy on the left, coming in from the upper left, is a single-ended to differential converter. It's just a transformer and a balun because the chips use differential signaling. The right-hand side, the pink foam, is a TCXO mounted on a circuit board wrapped in foam for temperature stabilization. Because even though it's temperature compensated, put your finger on it and watch what happens. There's an antenna splitter, GPS antenna splitter, the GPS module itself at the lower left, another one of the converters. So I did all sorts of testing with this. This is essentially the same circuit and design that we're using in the clock module, but this let us test it before we had to build any. These are some preliminary results, and I'm not going to spend a whole lot of time, but just noticing this is probably the most interesting. This is the frequency accuracy, how close the output is to what it ought to be. And the red box, the blue is the expensive one, the violet is the middle, and the green is the cheap one. And they're both down to parts in 1 to the minus 13th when we look over an 18-hour averaging period. So all 3 of these can get you extremely close to the correct frequency. How much noise there is getting there is a little bit different, but they're all capable of very precise frequency output, and they're also capable of very precise pulse per second output for the timing. And as Nathaniel and others mentioned yesterday, the frequency accuracy and the timing are really important for a lot of the science applications that we want to do. And we've designed the entire Tangerine SDR to provide that. The clock module gives us the basic performance that we need to be able to meet those goals. This is the stability, and this is an Allen deviation. I won't go into the details, but the bottom is taking measurements at X time apart, taking a measurement every 10th of a second on the left to every 100,000 seconds on the right. So longer, when you look at 2 measurements, how different are they likely to be? And that's the value on the left. Lower is better. The main thing I want to show you is that here's where you get your money's worth. The blue line, again, is the expensive one. The green line is the cheap one. And there is a noticeable difference. You do get some benefit for spending the extra money by buying the gold one. It will also sell you a service plan. This is a phase noise. This time I'm comparing it with the Leo Bodnar GPS DO because Leo uses a very similar design. He was out first. I don't claim that I invented this. Leo came up with it independently before I did. And he sells a very good product. I really like the Bodnar GPSDO for the money. It's great. It does some good things. You can see our performance is roughly similar. Again, I've got these spurs that I think are the test system. But Leo is a little bit better on the phase noise. He's also a little bit better on stability. And I think the reason for both of those things is he has more space to work with. His TCXO was not 3.2 by 5 millimeters. And I think that allows him to get better performance than we're able to given the constraints that we have. We've talked about the clock module going into the Tangerine SDR, but I am one of the time nuts and I would like to be able to use it for lots of other things. So we're designing, and TAPR will be offering, a standalone unit that's sort of a life support system that does all the things that the clock module requires and makes all the outputs available. So this board will give you all 10 frequency outputs on SMA connectors. You can plug in an external frequency reference if you want. You get PPS. There's a microprocessor on board that we need to use to boot it up, but after that you can potentially do some other interesting things with it. So it's designed to make the time nuts happy, and I'm looking forward to that. If you're not a time nut but you're a ham, and in particular if you're a VHF, UHF microwave ham, think about having 10 outputs that you can program to anything up to a gigahertz. Think about local oscillators for transverters. Think about beacons. There's a number of quite interesting ham applications for this. And finally, I want to put in some truth in advertising. This design was optimized for the Tangerine SDR. It doesn't really meet laboratory performance levels. There are two limitations. One I've already referred to is the TCXO stability just isn't all that great because of the space limitations. Secondly, the jitter attenuator chip does not have a narrow enough bandwidth to take advantage of a better oscillator. If you have a really good oven oscillator, you want it to be in control for periods out to a few thousand seconds because it will be better than the GPS. And so you need a narrower bandwidth. The jitter attenuator chip can't do that. So the two of them together mean putting an oven-controlled oscillator on doesn't really buy you anything, and you'll never be able to get the kind of performance you can get out of some of the standalone GPSDOs. So it does have some limits. As an option, you can plug an external reference in and just use the synthesizer and only have the 10 separate outputs. And you can tweak some things differently to optimize that environment. So that is pretty much what we are talking about. Steve, how am I doing on time? Oh, you're doing good. Okay, so I'm now going to segue a little bit into a related project. This is the Universal GNSS Listener Interface, or the UGLI. I came up with the acronym and then decided to design something to do it. This is mainly to address the fact that if you are experimenting with GPS modules, you can buy all sorts of little breakout boards from people like SparkFun that have the module and have the antenna connector and a USB connector and often the pulse per second. But none of the boards bring out all the lines that the receivers are capable of. They also don't allow the kind of configuration flexibility that you want, and you need a separate board for every GPS. So this is designed to be a Swiss Army knife kind of thing. It's a main board on the bottom and then a carrier board that plugs into it that the GPS module is actually mounted to. All that is on the carrier board is the GPS, the antenna connector, and a little power protection circuit for providing power to the antenna, LNA. And it gives you everything. This has 6 SMAs if you want. 4 of those are buffered pulse outputs. 2 of them are timer inputs. If the chip supports it, you can feed a pulse in and it will timestamp when it happens. The upper right is the USB connector that goes directly to the chip. The upper left are 2 voltage regulators. You can use any voltage up to 15 and select whether you have a pre-regulator first to get to 9 volts, then to get to 3.3, so you spread the heat dissipation out, or you can jumper that however you want. Then along the left side is another USB port and an RS-232. There are UART to USB and RS-232 converter bridges on the board. So the U-Blocks modules have additional output and input than the main USB. You can plug that into these and get old-fashioned 232 or a USB. And because there is no problem so big or complicated that it cannot be over-engineered, there are lots of holes. You can basically route any of the datacom signals from the GPS to any of the output pins of either the RS-232 or the USB, or just bring them out separately for I2C or whatever you want. So the idea was that this thing doesn't limit what you can do with a GPS module at all. Whatever the module can do, this will let you get at.
I'll give you a 5-minute warning.
Okay, perfect timing. So let's see. This is just more of a close-up. This is actually, the bottom board is the UGLI extension receptacle, or the uglier. And you can just see a better view of all of the different options that there are. The 2 headers on the right are where the GPS board plugs in. It's got a battery for clock backup, et cetera. We're going to have the carrier boards available for the NEO-M series, and that's finished. We're ready to start selling those. There's another footprint it's called the LEA that has one variant that actually is sort of a GPS DO all by itself. So we're going to have a board that'll take that, and then also a board for the more expensive dual frequency receiver. Both of these are going to be semi-kits. All the surface mount parts are installed. The user installs the connectors and the headers. So the main board, the uglier, is not too bad for assembly. However, the GPS module itself is a little bit more challenging. The NEO and LEA versions can be hand soldered. They're surface mount pads, but they're fairly large and not too hard to solder by hand. The Z chips, though, have pads under the module, and you cannot hand solder them. So that's going to rule out a lot of people from being able to put this together. So what we are planning to do, and I should actually move to the next slide because I think that's where I talk about it, is TAPR is going to put out a request for pre-orders probably to both the Time Nuts and the Hamside mailing lists. If we can get 25 people or so to pre-order the board with the ZF9, and another 25 if they want to order the Neo M8, I think we can get those contract manufactured with the modules installed, so you won't have to do that. So in about a month or so, I hope we'll be able to put out that request, and I'm still waiting to find out what the cost will actually be. I think this will be quite inexpensive. The main board is certainly going to be less than $100 as a kit with the connectors included. The carrier board, I shouldn't give away the manufacturing secrets, but I got 25 of these from China, minus the GPS module and the connectors. 25 of them delivered, including shipping, for $130. So they're pretty cheap. The cost is the GPS module and the assembly of the GPS. So we're working on it. You will hear more. If you're interested in GPS experimentation, I hope that this will end up being a really useful tool. And we'll add additional GPS modules if they come along and people are interested, additional plug-in boards. That's it. Thank you.
Do we have some questions for John?
As usual, there's just stunned silence.
Oh, no.
Go ahead.
Hold on.
As a fan of Trimble, do you have any plans for Trimble carrier boards?
At the moment, no. I don't have anything against them, but we've been focusing on the U-blocks because of the dual frequency, and we know about their frequency output capability. But if there's interest, and we can get the footprint and the signals, it's no big deal to create a board for them.
Okay.
So we can talk about that if you want.
All right, thank you.
Anything else?
Any additional questions up front?
Yeah, I noticed the carrier board there is different than the clock module for Tangerine. Is there a possibility to using the one on the other?
I don't think so. The clock module makes important I/O available, but it's really focused at an RF synthesized output. This is more focused at positioning and pulse per second timing. We could put different connectors on, but I don't think it would be economically practical to do that.
Any others? Well, thank you very much.
Okay.
Okay, so that pretty much completes the talks for today. And we thank everyone for their submissions of the papers for the proceedings and also being present for the DCC. What we'll do now is